Okay, so this is UCLA QC Bio Collaborative Workshop 1C, Advanced Unix Scripting and Queuing for Large Data for Spring 2025, second day. So we will continue where we left off, which was most of the way through the day one slides. So you should also have from email an hour or two ago the part two. The slides are really part one, two, three. Don't necessarily line up with day one, two, three, but you should have the part two slides and the text file that goes with those as well. But for the moment, we're back on the day one, the part one package. So you should still have, we don't need to do another huge copy like we did last time. So get back on Hoffman and use the same resource requirements that we had on day one should be fine. So wherever the slide is from day one here, this is the resource requirements that we were using. So get on a compute node. And then looks like slide 32 was where we were. Okay. And then change to your scratch space because that's where you did the copies yesterday. And you have this W1c directory in your scratch space, and it looks something like this. This is the way we left it. Okay. So our first task today is to basically split those into pieces and then start the alignments and so on. Yes. Let me see. Yeah, okay. So let's do that. To decide how to split them, we sort of need to know how big they are. So I kind of gave general stats the first day, but the way to tell would be to do something like this. So we just do a little for loop over the two input files, and we make a temporary uncompressed copy to standard output, pipe that to the word count program. WC is the program that counts characters, words, and lines. We're not much interested in words, but characters would be the uncompressed file size if you were to uncompress it. And lines is interesting for us because that would be related to the number of reads because these are FASTQ files. And uncompressed, you would have 4 lines per read. So if we take the number of lines and divide by 4, that would be the number of reads. Exactly. We don't want to round anymore. We want to know exactly how many. So this little for loop would produce we'll call them word count files. We'll just remove the .gz extension and put WC there. And we could do them in parallel in our session by putting that in the background. And we can start that off. It's just that they're going to take a few, like 20 minutes almost to do that. So we won't wait for those to finish because we actually already have the outputs for those ready. So we'll let them go, and we'll have 2 jobs running there. And they are producing the word count with the capital WC files, but those are empty yet, and it'll be 15, 20 minutes before we get those. But we also have the lowercase WC that you got when you copied this directory, which has the result already ready. So it's kind of like a cooking show on TV. We've already got, we just put it in the oven, and magically we already have one magically ready to take out of the oven already. So if we look at those WC files with lowercase, which are the ones that are already done, we can see that the order that comes out of this thing is lines, words, and characters. So how big are these files uncompressed? Well, that's the second group of 3. That's the third group of 3. That's 147 gigabytes uncompressed, and this guy is 114. So the total uncompressed size for those two is about a quarter terabyte. So, but if you see that they're on disk, they're only more like 70 gigabytes. So you see their compression is a big win because the compression is like 3.5 times smaller than the uncompressed version. And that's why we're always so concerned, especially in bioinformatics, where a lot of files are text and very compressible and so on. That's why we always do compression, because it's such a big space win. But here's the numbers that are related to the number of reads, right? Because these are the number of lines. And we know we just got to divide by 4. Well, there's only 2 samples here, and that's easy enough to pop open a calculator, divide by 4 or whatever. but you could do that in the shell too. So here's a little shell function that will just take a bunch of arguments, pay attention to only the first one, and divide it by 4. So if we feed it this first number from here, that divides it by 4. It's the same calculation we just did in the calculator, right? So if I take this, divide by 4, there it is. Well, that's only halfway automating. The thing is can we just get the number to directly show up here directly, so we just get a file with the results. So here's the little for loop to do that. We loop over the two WC files, and for each of those, we figure out how many reads there are by dividing the first number in that file by 4. So how do we do that? Well, we want to call this shell function and give it the first argument, which is the contents of the file. So this shell argument is expecting it in the first argument position. It doesn't, this shell function doesn't read a file or anything. It just wants the number right as a command line argument. So what we do is we use the process substitution, the $ with the parens, and we put a cat of the file in there because the cat in the file will turn into the contents of the file. And then the substitution here will make the contents of the file literally be the arguments to this function. And then that will produce on the way this thing produces the output is it echoes it out. So the output number we want, the divided by 4 number, comes out as standard output from this as an output, but then we need to do the same thing. So we capture that, we do a little process substitution with this so that we capture the output of this thing and make it be the right-hand side of this equals. And so the shell variable n reads will end up getting set to the number divided by 4. And then we just make an echo statement that just produces, like puts the name of the file next to the number of reads. So it's nice. So let me not include this little part at the end. So let's just do that for loop and see that work. So we'll just do these lines, but not include the redirection at the end. And there you can see what's coming out from this. The final echo here, which is producing this output, is echoing the number of reads that we just calculated. A tab, this is a horrible looking thing, but it really just is a way to put a tab inside a command line. You can't really put a tab in there because you may know that's how you get tab completion in the shell. So like if I do like cat RA and I hit tab, you see it completes to ND because in my files I have RA, the next unique completion is ND. If I hit tab again, it'll actually tell me the possible completions. And then if I type enough to uniquely determine the rest, like 01 and hit tab again, it will type the rest of it for me. So tab is sort of bound up with things like tab completion, and it's kind of white space and it behaves funny. So you always have to do something special if you actually want to get tabs embedded into a command. And the crazy syntax is this. This is just another fancy quoting. Instead of a single quote, you put a $ in front of it, and then what happens is everything inside can understand backslash escapes, and backslash T is the name for tab. So this is just basically a tab. So we produce a number of reads, tab, and then this is the file name. But we'd sort of like the read counts to reflect the original file names and not the WC name. So this strips off the .fastq.wc and puts .fastq.gz on. I suppose since the fastq is shared, it would have been the same to do this. This is equivalent here. We just pop off the .wc and put a .gz on instead. We are very familiar with these days of the if you have a shell variable set to a value and then you do this, you get the value. But that expansion has all kinds of substitutions it can do as well, string manipulation. And this % means remove the tail suffix if it matches this. So this looks for a .wc on the end and strips it off. That's what the % means. It's a suffix deleter. So that's what that's about. And so that's very nice. That gives us like a little, this little for loop gave us a little two column tab separated file, a little table. And so we could capture that in a file because that's kind of nice to have. And so we just redirect the output of the for loop into a file. Okay, so that way we capture the output of our little table here. And so now we have this file num reads by file name. And for example, other things in the future can read that if they need to know the number of reads or whatever. So this is kind of nice. So this would have, with 2 samples, not a big deal. This would have worked with 100 samples where you really wouldn't have wanted to do it by hand. Okay, so that's all great. So we did that. Okay. So next What slide are we at? Gotta expose a little more. That's this one. Okay. Okay, so now these are too big. Even, the methods we are going to show will work with these files perfectly fine and just produce a lot more parts and so on. But to kind of keep the runtime a little bit under control for the live demo, these are too big to kind of deal with as a whole. So we're just going to cut them down to their top part. So, like we just figured out that this guy is 450 million reads and the other guy is 350 million reads. And it just takes like 20 minutes to go from one end of that file to the other. So anything we do with it, split it into parts, whatever, it's all going to take like 20 minutes and we don't want to wait that long. So the first thing we're going to do is just for the purpose of demo, cut down to the first 10.1 million reads, okay, which is about a 40th of the size of these files. That's just to make what we do go faster. But as I say, you could do everything we're about to do with the full files. It would just take longer. We need to cut them down. Okay, so we did the top half of this slide. That's the previous slide. We're working on the bottom half now. The bottom half is now just to cut down the files to the first 10.1 million reads each. Okay, so what we do is we loop over the two gzip files, the two big guys. We uncompress them into plain text uncompressed form. And then the head command from earlier, workshop 1A, I think probably you cover the head. Head just gives you the top of a file, right? So do we have any files that are in plain text and more than one line? Well, we've got these files. Maybe I'll use on one of them just to make this simpler. Okay, so now we've got this plain text file with a lot of lines, right? This rand o1txt is like this, remember, and it's like a million lines or something. But if I do head, that by default you get the top 10, but you can say head-n whatever you want, and you get that many lines, like 3. Well, we can do the same thing here. We want 10.1 million lines. So sometimes, we could literally just do that, right? So 10.1 million would be this. That would be that number there. And that would be perfectly fine to put here, and you wouldn't have to have this arithmetic. Well, actually, that wouldn't be right. You have to multiply by 4, because remember, it's a FASTQ file. So if you want 10.1 million reads, then you need 40.4 million lines. So we would need to multiply that by 4 to get the number of lines that we need to keep. So that would be perfectly fine. I tend to find that when you get numbers with a lot of digits and it's sort of like, it's too easy to make a mistake where you get the number of digits wrong. And so I often just throw in shell arithmetic to make it very clear what the number is, right? So now I'm doing arithmetic in the shell, 10,000, 10 million plus 100,000, right? So that's 10.1 million in a way that it's very easy to read that you got the number of zeros right. And then we put that in parentheses, multiply by 4 to go to number of lines instead of number of reads. But that's all this does. It's just sort of a shorthand, it's a longhand way of writing that number, but it's sort of easier to verify. It's sort of, you didn't make an arithmetic mistake or typing mistake. Okay, so that gives us the first 40.4 million lines, which is the first 10.1 million reads. We re-gzip that. Let's do gzip fast today. And then we're going to put that in an output file because that will become the new starting point for all the work we do. And we're going to construct the file name of this thing by shortening things. These file names are also a little long. It's nice to have file names that are very descriptive. This file name actually kind of describes the origin of this file, this SRX, if you know NCBI, that already tells you this is a short read archive accession ID from NCBI. But this is actually the concatenation of a whole bunch of runs. And so these are the NCBI SRA, SRR run IDs that they come from. Well, we don't really need those to carry through the entire analysis. Let's just use these. These are unique IDs already for these samples. So let's just cut them down to this. So we just used another little shell transformation with the percent. Remember, the percent is the suffix deleter. And what you can put here is actually a whole shell pattern. It doesn't just have to be a literal thing. So what we're saying is look for a double hyphen and then star. Just like when you do path name expansion, stars match anything. Like when I do that rand star, that will match all the rand files. That's the same star that's here. And so what we're saying is look for double dash anything and kill everything from there. So we're basically finding the first double dash and then everything to the end goes away. So that is that's going to kill all this stuff here and just leave us with this first little sample word. Yeah, question?
Oh, you're saying you're keeping.
The percent activates the prefix deleter. Then after the percent, that's the pattern to look for to tell you where to delete. So yes, because the pattern matches double dash anything. And so if you look, where are the double dashes? I think there's only one double dash in these, so there's not even a confusion about which one it would pick. So the only possible place that pattern can match is here. And then because it's the percent operator, that means kill this suffix. So then we're left with this, what's the leftover part. So and then we'll add a new suffix after that, right? So then this is just the sample SRX, blah 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 7 or whatever. Then we're going to put like dash head. The dash head is a reminder that we cut this down. It's no longer the full sample. But this is now a gzip FASTQ file. So we put the .fastq.gz back on. And then let's do the two of them in parallel. So we put that in the background. Okay, and then so let's kick that off. Now we probably still have two jobs running right now because that's the word count guys on the big guys. They're still going for another 10 minutes yet. So that's all right. We're just gonna kick these off here. And now we got 4 jobs running. And we should start seeing the outputs building up already, right? So here's the outputs, right? This one and this one. And you see that they're kind of small right now, but if I list again, they're bigger now. Okay. Now they're not gonna grow to anything like these sizes because, like I say, they're like a 40th of the size of the originals. We could kind of estimate, while this is busy, if I take the number, this is the byte size of the big guy, and the big guy is how many reads. We figured that out just a second ago. Oh, it's maybe even already on the slide still, right? Oh, it's here. This is how many reads in the big guy. So I'm going to divide. That's the average number of bytes per read in that file. And assuming the gzip is about the same, then if we multiply by how many reads we're making here, which is this is read count based now. So that's the number of reads we're expecting to make. So we're expecting a file size of roughly a gig to come out of this. That gives us just some idea of when we're going to be close to done. Well, actually, by the time it took us to figure that out, they finished. But guess what? The file size that they come out to be at the end, a gig about. So that all tracks. We could, look into one of these just to kind of verify that they look right. Yeah, okay, they look right. We could gzip on one of them and word count them, and just to see if kind of they're the right length or whatever. But it's pretty clear that these two worked. So this shouldn't take anything as long as the big WCs, because as I said, these are a 40th the size. So should be like 30 seconds at most. Okay, we'll let that go. I guess on the slide I was going to monitor them while they run, but they finish so fast we don't have to do the monitoring. And we saw those commands yesterday anyway, so we don't have to worry about that. Anyway, yeah. So anyway, so 40.4 million lines, exactly what we expected. Okay, so that's all good. Okay. I won't do this because we want to move on. If you really are in a situation where you're really doing research and you need a smaller portion of a file, like you want to do like a test run or like a statistical analysis on a subsample, you would not just pick the top of the file, right? That's a bad idea. You really want a random sample of the file. That's inconvenient to do with like the base utilities. But in my home directory, there's this program I wrote years ago that picks out random subsets of lines from things. And what you do is you give it 2 command line arguments, how many lines you want it to pick, and how many lines are in the input in total. By giving it the number of lines in total, it doesn't have to go through the file twice and first count how many lines are in the file. It can just, you told it how many lines there are, and that way it can actually go through the file just once. Because there's a nice way to kind of do that random subsetting in a streaming way where you don't have to read the whole file into memory first and then like pick out the lines. You can actually decide as you get each line whether that's going to be in the final output or not, as long as you know how many lines are in the whole file. So you give it those two command line arguments, and then it just acts as a filter from standard input to standard output. So you can feed it in a big FASTQ file, tell it the number of lines you want is 4 times the number of reads you want. The second number is the total number of lines in the file, 4 times the total number of reads, and it will spit out a random sample, which is like that. Well, it's line based, so you have to first do the trick we did yesterday. So you would take the gzip file, the gzip FASTQ file, uncompress it, do the paste trick we saw yesterday to get it from a 4 lines format to a 1 line per read 4 column format, because this tool is a line based tool. So you don't want to take like the read names from one read and the read sequence from another guy. You got to keep all the 4 lines of a read together. So the easiest way to do that is to make those all be wide lines so that you can just subset the lines.
So if you run this twice, same.
You will get different output. Yeah. Internally, it uses a random number generator that depends upon the entire state of the Linux machine. So random interrupt timings and so on. So yeah, it's designed to be, and it's designed to essentially be a perfect random number generator. So it's a very high quality random subset. And if you every time you run it, it will produce a new random subset. Then once you get the output from this, which is line based, then you want to change the tabs back to new lines so that it's back from a wide format back to the 4 line format. Then you can gzip it. Anyway, you can play with that if you want or whatever. But that would be a true random sample. And if you're actually doing research quality work, that would probably be a better idea than just the head. But we're just going to take the head. We're only using this data just as a way to learn about the queue system and how to handle large shops and stuff. So we're not too worried about the actual biological relevance of what we're doing. And also, like, if you really get into like stuff like pipe viewer, so pipe viewer is not going to be in your session today because remember, it's not part of Hoffman, so you have to run that little command I had yesterday. It's another program in my home directory. So somewhere we had this line here, which puts it in your path so that you can use it. All right, so
You have to download that.
you could download it and compile it in your own directory. You could copy it out of my directory, or you just use it out of my directory, or whatever you like. That's what I did. It's a C program, I think. So you download the source and compile it, but depending on your experience with that kind of thing, that's either difficult or not difficult. And then, so here's a pre-compiled version ready to go. So, so we've got it's working, but to make it work, you got to go back to the slide, day one and find this line, highlighted line right here. So you can get really crazy with pipe viewer. Like I'm not really expecting you to kind of get into pipe viewer anything like this, but I'll show you like how crazy you can get when you kind of get into it. So you can actually remember pipe viewer is the thing that makes a little command, the text mode progress bars. So if you do like stuff like this, you can even get like multiple progress bars for jobs running at the same time. So here you will see that I'm getting 2 progress bars simultaneously. We're running the 2 jobs in parallel, and we have text-based progress bars for each of them. So I really shouldn't take the time to. It's no point in explaining this command line. But anyway, I just want to show you that it's like it's possible, but that doesn't mean it's this is really kind of you have to have a real high facility with things to kind of be able to whip these out and have them work. But yeah, I mean, you don't really need to get this fancy to get a lot of stuff done. So, all right, time to actually split into pieces. I think I have to let this one finish because I think it's overriding the ones we had done just a second ago. So I do have to let this finish. And I think one of our WCs finished as well. There was a done message a second ago. Scrolled off the screen already, I think. No, actually, everything might be done now. Yes, everything's done. And if you look at the WCs, so there's the 2 that were pre-baked. These are the 2 of ours, and there's the same output. So, okay. All right, so how do we actually do the split? Okay, so yeah, so this is just verifying that the cut down was correct, and we already did that. So the split is here. So the nice base command Unix utility for splitting text files is called split. There's a man page for it. You can say split --help. It has stuff. There's quite a few arguments that are actually pretty relevant. So, but we'll just look at the ones that we need here. So we've got two files we need to split. So we do a for loop over the two files, the two samples. Okay, that's this. So now X is the current sample. We gunzip it. Split is plain text based, not gzip. That's fine though. We can feed it from gzip. So we gunzip, produce an uncompressed copy into this pipe. Then we're starting split, and we have to tell split. Split has defaults, but we kind of want them a certain way, and the command line options have quite a bit of flexibility how you want the files that come out to be named. So you get to decide how many, you have to basically tell split how you want it to make the output file names. So the output file names are going to be some kind of prefix, and then some kind of serial number that split's going to make, and then some kind of suffix, right? Something like this, right? So we got to tell it how to build those parts. So first thing you have to tell it is how many digits do you want in the variable portion, okay? Which is related to how many parts you're going to make. Okay, maybe we should talk about how many parts do we want? Well, just as a demo, these parts are actually going to be too small when you get to real work, but I want to have like a dozen parts in each file. So if the files are like 10 million reads right now, let's cut them into 500,000 read pieces, okay? Because 500,000 into 10 million is 20. And then the reason why I'm doing 10.1 million lines instead of 10 million lines is because I want to show you what happens when you have a partial piece, right? Because 500,000 goes evenly into 10 million, but let's do 10.1 million so that we have to have a 21st part, and the 21st part is just 100,000, right? So I don't want to, it's too clean if it kind of divides in evenly. That'll never happen in real life. So let's have the last parts be partial. So we'll do 500,000 read parts, and there will be 21 parts then for each file, because 10.1 million 20 parts gets you to 10 million, and you'll need a 21st part to get that last 0.1 covered. So how many digits do we need for our file names then? Well, I mean, you could use 4 or 5, that would certainly be enough, but 2 would be enough for us. We only need 2 digits for 21 parts. So suffix length, and I just did this to kind of make a little, a little more clarity, but you could have just put in 2 here, right? So you could have just put 2 here and whatever, but the 2 is here. Anyway, we want 2 digits in our file names. And a lot of programs have both long form options and short form options, right? So like suffix length is also known as -a. So you could have done this as like this, which is easier to type, but a lot of times, especially when you've got shell scripting and stuff like this, I kind of recommend the long names because it will help you just look at this and you know what it is. It's like -a, you're going to forget what that means, right? But -- suffix length, that's a lot more obvious what the purpose of this is. So it's a trade-off between typing and memory. So anyway, so we want 2 digits in our serial numbers. This says that we want the serial numbers to be numbers. So by default, actually, I think it scrolled off, but I said the file names it's going to make are something like this. Literally like this. Okay. So the question is, what is the number? For us, it's actually only 2 digits because we just asked for 2 digits. So is that going to be like 00, 01, 02, 03? Or is that going to be 01, 02, 03, or 04? Or actually the default in split is to use like AA, AB, AC, AD to AZ, and then like BA and stuff. So I don't know why the alphabet is the default, but it is. It's just tradition. So --numeric suffixes says I want them numbered and not lettered. And then the =1 says I want you to start counting from 1. I think the default is actually to start counting from 0. But this means start counting from 1. Use numeric numbering and count from 1. And then this additional suffix is the part after the variable part. So we want them to be .fastq. Not .fastq.gz, because split is going to be making all these files, and split is receiving uncompressed fastq. There's not really a way for split to write compressed files directly. We can't get like pipelines in there because split is the guy that's going to be opening up and creating many files, each of which would need to be individually gzipped. So we're just going to have the split parts be ungzipped first, and then we'll gzip them in a second. But so what comes out is .fastqs, not .fastq.gzs. Okay, the next parameter split needs is how do you want me to split? Do you want me to split every megabyte? Do you want me to split every 1,000 lines? What is the criteria for how I'm breaking these into pieces? We want a line-based split, and we want a certain number of lines in each piece. So that is the double dash lines argument, where you give it the number of lines you want. And if we want 500,000 line pieces, because it's 4 lines per read, that would be 2 million lines per piece. But let's just do the shell arithmetic again, right? So that's 500,000 reads times 4 lines. The verbose will just make split produce progress. Every time split produces a new part, it'll give you a line, so you just see something happening. This is the input file to split. So if you already have the file on disk, you could have, put a file name here, but we want split to take its input from standard input from a pipeline, because we need to feed it a gunzip thing. So the dash there is just many programs understand this convention for input file names, but it is a convention. It's up to the program to decide what it means. But many programs have the convention that a single hyphen means standard input, and split is one of them. So this tells it split, you're getting your input from what's, the pipeline that's feeding into you. And the final part of the command is the prefix. What is the part of the new file names that occurs to the left of the variable portion? And so for us, that is going to be these file names that these things we just made. I see what happened. When I did the pipe viewer one, I actually was thinking ahead when I made the slides, and I actually named them differently than the first round. So actually, I didn't have to wait because they didn't overwrite the old ones. We made 2 copies now. That doesn't matter. Anyway, so this is going to be the input file, like X in this for loop is going to be this once, and it's going to be this once. So X is something like this. And so it makes sense that the thing to do is just pop off the .fastq.gz. So the new part names we want are something like SRX 101.207 SE-head -part, and then the number, and then the .fastq. So we need to pop off the .fastq.gz. So we do a little transformation, X suffix deleter, .fastq.gz. So that's now this. And then we're going to put -part. And then split is going to fill in the number, and then it's going to put on the additional suffix. Then it's going to put it on the .fastq. Okay. So let's run this. And we'll do the 2 splits in parallel. Okay, so then finally, I could have just not put the ampersand there. We would just do the first split and then the second split. This will run the 2 splits in parallel. Okay, so here I got I got the 4 already. Okay, so these 3 lines. Okay. Oh, is this because? Okay. Never mind. Let's not do them in the background. Let's just do them serially. Okay. The problem there was that when we ask for progress, they're trying to fight for output to the terminal, and it's causing I don't want to get into that right now. So we'll just do them serially. It's not that slow. It's pretty fast. So you see, and now you see the file names that it's constructing, which is exactly how we just explained them. Okay.
Yeah, if it's not randomizing.
No, because here we're using the head part is already done. Yeah. We chose to do it that way. All right, we finished the first one, 21 parts as expected. We're on the second one. Of course, if you were doing the unsplit files, probably need 3 digits, and you're going to have, well, we can figure out how many pieces it would be, right? While we're waiting here. So it's the big guy is 451 627 615 reads. and we're doing 500K pieces, 903 parts it would be. And that would be fine. You just would increase this to 3, right? And wait longer. And hopefully you have the space, the quota space for it, right? We know that the uncompressed split copy is going to increase your quota by exactly the uncompressed size of these guys, which is 147 gigabytes for the first guy and 140 gigabytes for this guy. So if you were to do the uncut down guys, the splits would be adding 261 gig to your quota. We're gonna immediately reduce that though, because the next step is to gzip them back down. Oh, okay, we're done here. So okay, so if you look in our directory, we now have a lot more files, and we've got all these guys here. And we could look at them and verify their line counts and stuff is correct or whatever. I mean, we could do, let's do the shorter one. So we could do, give me the line count for all those guys. 2 million as expected, right? Because that's 500,000 times 4. So, and then the last guy should be 400,000, right? Because he's 100,000 reads times 4. So yeah, that's all as expected. So that looks good. We've got the parts. We would like to gzip them. We just verified, yes, the split worked. And we would like to gzip them now. Okay, so these are just going through more different ways to check that things work. Like this one is looking at the first 8 and last 8 lines of every one of those files just to see what the heads and tails look like. So, I mean, this just all you can do as paranoia of checks as you kind of feel you need to do. So, but it's pretty, you know, these worked. Okay, so we don't need to continue checking. I guess I went through a whole nother slide about checking how paranoid you want to be. Like a strong test would be to actually reconcatenate these and verify that you get exactly the same starting file back. That's a strong test. So you could do that check by actually like literally concatenating them and comparing the files. But like one thing you could do is you could make what's called a hash. So programs like SHA sum and MD5 sum will take an input stream and grind it up with cryptographic techniques into just a number. And then if the two numbers are the same, it's highly, highly likely that the entire files are the same. That's the purpose of these hashes, is to be kind of collision resistant, and small changes make big changes in the number. But because they are very short numbers, there are collisions. It's just very, very unlikely to ever find one in practice. Or you could literally go to the trouble of like literally comparing that the bytes are completely identical. So to save time, I won't go through this, but if you kind of, if this check, a lot of people are satisfied with this check, this is a little bit more checks, this is the real check, right? So this is like literally verifying that you take the parts and reassemble them, you get the original. So let's skip that. So here is we've got a problem though. We would like to gzip these. We could go to the trouble of making Hoffman jobs. We haven't even done Hoffman jobs yet in this workshop, but we're about to. We could do like a gzip job for each piece here, because especially if we had 1,000 pieces, right? That would maybe be the way to go. I don't want to do what we did yesterday when we talked about backgrounding jobs on one node. So this would be a bad idea right now. So like if I do a for loop over all those .fastqs and I want to gzip them and background them all, this is a bad idea right now, because this is now 42 simultaneous gzips, and our session is only for 3 cores, and this is just sort of like too many. And if we had 1,000 parts, this would really be a bad idea to try to do them all simultaneously. So is there something that one can do? I mean, if you could do this would work, but it's slow, right? You could give gzip all the ones at once. It's just going to do them one at a time with 1 core each. The question is there something in between, right? So is there a way to do backgrounding that doesn't just start them all at once? We really want some kind of moderated thing, right? So if we know that we have 3 cores, we want something that says, okay, here's all the ones I got to do. You can do 3 at a time, and as each one finishes, you can kick off the next one, but don't run more than 3 at a time and keep going until you got all of them done. And there's a very nice helper program called xargs that is one of the things it does is explicitly for stuff like that. So I'll show you that. It's it's pretty cool. And this is a program that would work on your local machine too. And so often, if you've got like a lot of files to gzip on your local machine or something, this is going to be a great way to do it because you don't have the hop and queue system on your local machine. So the program is called xargs. It has help. It has a man page. It has tutorials on the internet. AIs will also compose command lines for you with it if you want. But it starts with basically what xargs really is a program that composes command lines. And so you give it sort of like the variable part of the command lines as its input and sort of a template, and then it plugs in stuff from the variable parts into the template and then kicks off those commands. So first, for us, we need to say what are the variable part of the command lines. For us, that's the file names that need to be gzipped. So this command just spits out the list of file names that we need done. You know the ls command. You are used to just doing ls by itself, certainly. You are used to maybe doing ls with a explicit list of file names, and then it only lists those files. But you know that ls often writes things in columns. Like this is weird. This is like for human, reading purposes. The -1 argument to ls says single column only. So that means give me just one file name per line. So this is going to be our input to xargs. This is the variable part of the commands that we want to compose. It is, file names can contain spaces in them and stuff and special characters. And it's a bad idea to sort of feed xargs like output where like carriage returns are the separator, because I think the default for xargs is really white space separation, and that's just asking for trouble. So we transform all those new lines to a null character. It's like the zero, if you know like ASCII, which is like 65 is a capital A and 32 is a space and stuff like this. This is the character with zero. It's just a character that is like basically never appears in file names can not contain a zero. And zero is a better sort of divider between the things that go into xargs than just random text. So it's not going to hurt us in the current case because our file names don't have any spaces in them and whatever and so on, but just good habit for xargs just to always use null terminated separator rather than new line separator. So this transforms our list to use null terminators rather than new line terminators. You're going to see that doesn't look very nice on the terminal, but if we were to try, like make the secret stuff visible here, like you can see that now at the ends of lines, there are, I could pipe that to less. We've now got like these 0 bytes at the end of lines instead of, if I take away that TR, the ends of the lines are like one of the ends of the lines is like, where is it? Part 1 dot fast right here would be the end of one of them. And you see this OA, which is ASCII code 10, which is, that's what the line feed is on Unix systems. So anyway, so this is what a normal text file looks like. This is this sort of like 0 bytes that we've replaced those line endings with. But this is the better way to feed xargs input. So, okay, so this now becomes the stuff we're ready to stuff into xargs. So then we say xargs, and the -0 tells xargs that, yes, your input is 0 terminated and not white space terminated. And then we give it the template. Okay, it's safest to put a double dash here to separate where xargs arguments are from the template. So the double dash says everything to the left is an xargs business and everything to the right is the template. So the simplest template we could just do is like some kind of echo command or something. And I'll do this just so that you see what happens before we actually do the gzipping. Okay. So what do you see? You see what happened is that xargs composed, in this case, a single command. That command is echo hello, and then it put, but if you don't tell it where to put the stuff, where do you want me to put the variable part that I'm reading? If you don't tell it, it puts it at the end. So it just took all the file names, turned them into individual command line arguments, and stuffed them at the end of this single echo command. And so then echo ran, and echo just repeats what is given as command line arguments. So there's the first hello, and then there's all the command line arguments. There was 43 command line arguments to echo. Hello, 21 from the first guy, 21 from the second guy. We want gzip to kind of work at one at a time, right? Because we want each gzip to kind of just do one, and then we can do 3 gzips in parallel on something. So we don't want commands to be packed full like this. Commands can get really long, and the default for xargs is to kind of pack command lines as full as possible. So xargs takes an argument n, which tells it the most number of things it's allowed to stuff into one command. So if I say you're only allowed to stuff 4 of them into a command, it has to run echo a lot of times now, right? So now you see it can do 4 at a time, but then it has to do another command at that point or whatever. And then with 42, it's not a multiple of 4, so the last echo only has 2 instead of 4. That's good. So I could just do n1, and that would now run the echo 42 times. And now we're basically at the point where we can kind of do the gzip. So I could do gzip here. I don't want the hello there anymore. That would gzip them, but it's still going to do only 1 at a time in serial order. The magic option to xargs is parallelize. So I could say parallelize 3. So now xargs will compose 3 command lines and kick them off in parallel. And as soon as any one of those finishes, it will then compose the next command line and run it in parallel with the 2 that are still running. And it will keep looking for guys to finish and kick off more commands until it has no more input to compose command lines with. So this is exactly what we want. I'll put the verbose on for gzip so we see the progress messages out of gzip as it goes. So there you saw 3 gzips kicked off in parallel. Each gzip is only going to get 1 file because that's what the -n1 will do. 3 of them in parallel. You see 3 gzips are working right now. And any minute, please. I should have said fast. There, the first 3 finished. And now, actually, they finished at about the same time because our pieces are all about the same size. So, but you see, okay, so this is the start of the first 3. That's a completion of one of them. That was, well, you kind of see it now. The left-hand half of the line and the right half of the line aren't the same file because they're delayed by, that's not going to happen because of the order. Gzip prints the first half of that message when it starts, but the second half of the message when it finishes, and that's delayed by a time. And we've got multiple guys running in parallel, so stuff can happen in the middle. So you kind of got to read the left-hand house and the right-hand house independently at the moment. But if you kind of look at it, every time one finishes, it kicks off another one. So, this is exactly what we want. If I were to get into another terminal session so we can kind of poke around in that directory while that's happening. Okay. I don't even need a compute node for this, a login node. We're not going to do anything serious here in this session. So here's what it's looking like as an intermediate, right? So here you see we've got some of them finished. We've got some of them in progress. Three of them, exactly 3 of them in progress, right? That should be the situation always here until we get to the end, and then we'll have 2 and 1 as the last one's finished. But this is what the typical intermediate step will look like. I got some of them gzipped, however many I asked for in parallel in progress, and we're just working down the list. And we're on to we can just do another ls here. Well, we got only 2 parts left on the first sample, and we're on the first part of the second sample. And this would have worked we could gzip thousands of files this way, right? And if we know if we're on our local machine and I've got a 8-core computer, I could do -p8 and I could be doing 8 of them at once or whatever, right? So there we go. Sample 1 is done, and we're working our way down sample 2. You could do like a watch here if you wanted. Like you could do watch star.fastq star or something. I guess it's too long. Doesn't fit on the screen. We could just do the .fastqs, then they would be disappearing as they go, right? So like now we're LSing every 2 seconds .fastq. Well, as gzip finishes a part, it deletes the fastq. So this list is getting shorter. This is the list of ones to do yet. So we can see them disappear here. All right, well, we'll take it's 2:30, so we'll take a 5-minute break. We can let this finish. You got yours finished? But it's making progress. You might need a second session to tell. Or, I mean, you should be getting progress messages in the main session, but if you want to look at the files, then you can use a second session. Oh, there we go. So Ashland's done. Oh, you're still doing the split. The split shouldn't be that slow. Oh, you got both running parallel. I think so, because I see 7 and 8. Yeah. Is it done? I mean, maybe it's done. Maybe it's been done for a while. Yeah, it's been done for about 14, 19. Because you backgrounded them. This is your shell prompt. Okay. They have been producing output while waiting for your next shell. You know what I mean? That's been your prompt the whole time. You weren't in a blocking mode. You weren't that wasn't waiting for. If you had done a wait and enter, you would have gotten prompt. But your prompt is up here somewhere. Yeah. Yeah, so actually, that kind of shows something I kind of mentioned on the slides, but I don't think I covered it, which is that the shell doesn't tell you job transition changes right away. It will only tell it to you by default at the start of the prompt. So you saw here, because you had already emitted a prompt, then you had output in the background, then jobs finished. But because you're not at the point where the shell is ready to kick out another prompt, you don't get the notification. You don't get these notifications yet. You can change that mode. So like, if you say set -b, this is called the shell option. Shell has all kinds of options. But this means notify me immediately always. So if you had done this and then done what you had done, these 2 lines would have been shown as soon as wherever they apply. So like, I mean, I guess the 8 finished first because he is a little smaller, right? So right after that, part 21, probably before this part 20, you would have gotten 2 finished, and then right at the end there, you would have gotten the 1 finished notification, and you would have gotten those notifications before reaching the next shell prompt. The default for the shell is the opposite of set -b and set +b. This is the default. That's the only notify me in between commit. Like when a shell prompt is about to go out, that's when it shells. I'm not quite sure why. I sort of think set -b is a little nicer, but tradition is tradition. So how we Sir Files, how are we doing on your side?
I'm not following along. I'm just listening to what you're saying.
Okay. I mean, hopefully you're getting some things out.
Yes, definitely, definitely. And it's exciting to learn all of these things because I wasn't aware of so many functionalities within this Unix.
Yeah, so one reason why the slides are so dense and so on is that they're intended for reference material afterwards. So
Right, right.
yeah.
There's a lot of information and it's really powerful. The things you can do using this with the shell scripting.
Yeah.
So,
What are you using? Are you on Windows or Mac at your place?
I'm on a Mac. I have a similar setup to what you have on your end.
Hmm.
So it's an M1 Mac with some 64 gigs, I believe.
Oh, it's a good size, right? You should play with the local AI if you haven't.
I haven't yet, but I was inspired when you spoke about it yesterday, so I might give it a try.
Yeah.
I'm just busy with a few things, working on manuscript and other projects. So, yeah, once I'm done with those, maybe I'll give it a try.
The one I'd recommend to start with is LM Studio, I think it's called.
Yeah, you mentioned yesterday LM Studio with Qwen 3 and Gemma 3.
Yeah. Oh, there we go again. I think I'm getting purple. My entire screen is blinking a magenta right now.
I can see everything.
Yeah, so that's just happens it doesn't happen on the projector, and it doesn't happen on Zoom,
Hmm.
but I've never seen it happen before, and I have to think that it's some interaction of like projector plus Zoom plus text edit. I don't know why that combo is bad, but it's done
Yeah,
it twice now. So
maybe it's the HDMI cable, or maybe it just needs a restart.
yeah, I don't know. It's weird.
Yeah, for me, we use Teams here at Cedars, and
Uh-huh.
it does some weird things every once in a while. So I just quit the meeting and rejoin, and other times I just give it a restart.
Yeah. Okay, we're ready to continue. We now have the parts. Jesus. If you were really tight on disk space, I suppose you could delete the originals at this point because the parts are equivalent. If you had to, you could reassemble the originals from the parts, but I would always recommend you never delete your original data. So hopefully you have the originals on external storage somewhere before you would do something like that. But anyway, yeah, when you do big projects, actually, this quota space limits usually become a complicated part of the management of the whole process. But where we have 2 terabytes of quota in Scratch, and we're using at most hundreds of gigabytes, low hundreds. So we don't have to worry in this demo about any kind of quota issues. Um, okay, so I won't maybe do this whole slide because I want to move on to the alignment stuff and so on. So, but when you are doing xargs, kind of how much you can do with xargs really depends on how well you can construct the input to xargs. So like here we just use ls-1 to construct the 42 file names that we wanted it to use it. But like suppose you had a whole directory tree, complicated directory tree with like, hundreds of files, hundreds of directories, nested structure, 20 levels deep, and you want to gzip everything in there, right? Well, then it's kind of how do you construct the list of inputs to xargs to get all that stuff? So a very powerful combination is the find command feeding into xargs. So, maybe I'll let you kind of go through this on your own if you're interested, but basically the first few commands on this slide just create a dummy, kind of a dummy directory structure with a bunch of files and a bunch of subdirectories and stuff. So now we have this tree directory, which has a subdirectory A, and it has files already inside of it, and they have different extensions and names. And then there's an E directory, and inside A, there's a BCD, and then A, that's got stuff. And then the A/B and the A/C and the A/D have stuff. So there's files all over the place in this thing. So then the find command is basically a super LS. It's an LS that can traverse directory trees, have conditions on what it shows, and so on. And so it's a great program to use to construct input for xargs. So like if I say find tree, look for the name anything.txt, find will spit out a list of all the .txt files anywhere in that tree. So that's the thing you can pipe to xargs and then gzip those if you want, if that's what you wanted to target. If you wanted to target every single file in tree, you could say type F. That's every file whatsoever. Type D is all the directories, but you don't gzip directories, you gzip files. So it's dash type F. It would be, if you wanted to gzip everything, it'd be something like that. You can put in condition, you can get all kinds of fancy things with the patterns. So like this is all the .txt's or the .tsv's. So there's a whole little language you can put in command line arguments to this find thing to control what you want. You can whatever, and then basically once you kind of get what you want, you can end with -print 0 so that just instead of putting out the new lines, it'll directly do the null terminated stuff. And then you just pipe that to xargs, and you can be gzipping, whatever stuff's like, yeah, let's do it. We've got this tree thing. So let's do find tree, every file, print 0, xargs -0, n1, p3, gzip. And I think these files are so small, I don't even need the project done, right? So now if I look inside tree, every file's been gzip. And those were done 3 at a time in parallel. So powerful combo, this find xargs combo. But find is a whole universe to itself, so I don't want to really get into it. I'll let you maybe explore this one on your own too, or I'll just give you the minimal demo here. But another alternative to xargs is GNU Parallel. It's sort of like a super xargs. It has a lot of features, and it also is into making text mode progress bars. So it is in the Hoffman module system. So if you say module load parallel, the command will become available to you, and then it kind of can work just like xargs. You feed it the same input that you would feed it to xargs. So I've got this tree that we just gzipped up, right? Well, let's ungzip this whole tree. So that's all the files in tree, which are all gzipped right now. And then I will print 0 that to parallel instead of to xargs. And then it will take like these arguments for parallel. So the -0 is the same meaning as xargs. The n1 and the p3 is the same as xargs. The options I've added are ETA, estimated time of arrival, and verbose. And now we're unzipping because that's what we're doing. And now you will see it's giving you a lot of progress. These are very tiny jobs, so that's why it scrolls by so fast. But you basically kind of see the kind of output this thing makes. It's based on the rate that things are happening. It's making an estimated of how many seconds are left, what files it's working on. It's like 2 are running, 66 have completed. You just get more information than xargs about the intermediate stage of the computation. So that's one you can explore. Okay, let's get ready for the bisulfite alignments. We've got our parted up fast queues. We are ready to do alignments on those, but we need an aligner. So first thing we got to do is we got to get bsbolt installed for you guys. So that is a Python program. So you may or may not already have Python stuff going on in your home directories, which I don't want to touch because Python can be fragile. If you've got something working for you for your main work, I don't want to disturb that. So we are going to use a virtual environment to encapsulate this bisulfite bolt installation, so it will live in just its own space and won't interact with anything you have outside. This also makes it more likely to work because we aren't going to depend upon the state of your Python elsewhere. So it's both to make it more likely that bisulfite bolt work, and it's also to make sure we don't break anything you already have. So bisulfite bolt installation does have dependencies, which the Python pip system can handle just fine. But some of those dependencies are in C, and they do need to be compiled. And the default C compiler on Hoffman is pretty old. So the first thing we do is we do module load a more recent version of the GNU C compiler, so that when the Python package system starts to try to compile things in C, it has a fresher compiler than the default on Hoffman. So this loads a recent, this uses the module system to activate a recent C compiler. Then we need a Python. So this is the most recent Python that's in the module system on Hoffman. Now we need to create the virtual environment. So let me check what directory I'm in. Okay, yeah. So you should be in the W1c directory of your own Scratch space. And this is the place we're going to actually it's an absolute path in this command. So it doesn't matter where your current directory is right now. So Python 3, that's going to be the Python we got from this. The Python module we want to activate is called VM. That's the built-in standard library virtual environment thingy. And then you give it the directory you want it to create the virtual environment in. So this is your Scratch space W1c, and then I usually name them something like this. This is a Python 3.9.6 virtual environment on top of GCC version 11.3.0. So that is a reminder of what you should have already module loaded before you try to use this thing, because it's going to depend upon those things. So that's usually how I name them. And this shouldn't take very long, but it's basically making a nasty directory structure down inside that directory we asked for. Okay, so if you look in here, we now have a new directory called that. And if you look at the files in there, there's a lot of them. We don't care what's in there. That's all structure this thing made. But then, so that line, which is in blue on the slide, only gets run once. You only create the environment once. The yellow lines you're going to have to do every time you use this thing. Okay, so the yellow lines are every time you use it. The blue lines are only the first time when you make it. The next thing we need to do is what's called activate that environment. We need to adjust our shell path and a bunch of other things so that all the Python-y stuff points inside this environment. And so there's a shell script that the virtual environment creation created, and it's in the directory where the virtual environment is /bin/activate. It's a shell script. It's not a shell script that can be run in the normal way, because if you run it as an ordinary shell script, what happens is when you ask your shell to run a shell script, it does not run that script commands inside itself. It creates another shell and then runs the script inside that shell. And then when that shell finishes, you're back to your own shell. And that way, whatever this script did does not affect your parent shell. All right. So if that script does all kinds of variable manipulation, who knows what, your shell environment does not interact with the whatever the subshell that ran the script did. In this case, we want to break that rule because we actually want our own path to be changed and stuff like that. And that's why we have to source this script and not just run it like a normal program. So the source thing here means it tells our shell, run the commands in this file in yourself. Do not make a subshell. You're going to let it affect you however it affects you. And so that's why we have to do it this way. But we're going to do that, and then you're going to see a bunch of things happen. The most notable thing that happened is that my shell prompt changed. That is just to help you remind you what you're like in this environment now. Okay, so it's a reminder. But the more important thing is that if you look at like your path, it's now like put stuff on the front of your path and stuff. It's changed a bunch of things in your environment so that you're now sort of going to take your Python-y stuff from this environment. Okay, so that's called activating the virtual environment. We now need to install bisulfite bolt inside this virtual environment. So this is back to blue stuff that we only do once. The first thing that's probably good to do is to upgrade the Python package manager because the default from Hofland is never up to date. So this Python pip module, pip is one of the package managers inside the Python default and install a package, upgrade it if it's already installed, which it is already installed, and then the package is pip itself. So this just upgrades the package, the Python package manager itself. And let's see. I'm not anyway. Yeah, this shouldn't take that long. Okay, there we go. Oh yeah, you see it did upgrade it. We were on 21.1.3 and it upgraded it to 25.1.1. Okay, so we now have a current Python package manager. We now ask it to install bisulfite bolt. Okay, so then the package is called BS bolt. And so this will take a little more work. This has quite a bit of dependencies. The nasty one that always seems to cause trouble is PySam because that generally needs a C compilation. So what you see here is that yours may or not have to download it. I think I've already downloaded them and it has a cache somewhere, so it didn't re-download them. But yeah, most of my stuff was already cached, so it didn't have to work too hard. Yours may have to work a little harder because it's probably the first time it's going to see any of those for you. But you see at the end here, successfully installed BS Bolt version 1.6.0 and 3 more dependencies, which it figured out. Now, when I tested this earlier in the week, this is a fault probably of the person that packaged bisulfite bolt. But the PySam, it's probably bisulfite bolt is probably saying, give me the most recent version of PySam that exists, which is 0.23.0 right now. But it turns out BS Bolt 1.6.0 is incompatible with 23.0. So that's really a fault of the person packaging it, that they should have tighter requirements on what this package requires so that it doesn't pull in something that it doesn't work with. So in this case, we actually have to downgrade PySam one major version here. So this is just based on empirical testing I already did this week. So we are going to downgrade PySam to this precise version because I know that works right now. So we are downgrading from 0.23.0 to 0.22.0.
We install both Is it like erasing the previous version or whatever installed?
I think the Python backend only prefers to keep one installed at a time. So that's uninstalling 0.23.0 and downgrading to 0.22.0. But it's all happening in the virtual environment. We aren't touching anything outside of it. And this kind of exact version dependencies is a very common problem in Python. And that's why pretty much every project you do in Python, you should immediately create a virtual environment and you just get everything right in that virtual environment for that tool. Because there's no way to do it simultaneously for all Python programs on your machine, right? Because program A may end up needing PySam 0.25.0 and this one needs 0.19.0, and that can't be simultaneously installed. So without a lot of work. So these virtual environments are very handy because you basically just isolate each major Python program into its own universe, and then that universe has just whatever combo makes that program happy. And your two different universes don't have to have the same versions of everything.
So when you do like install, you can put the entire line of like all the programs you're trying to install. And then second question is.
You can do that, and actually when you do that pip install, pip is actually doing a huge amount of work. It's actually like, it actually goes through like a combinatorial explosion of possibilities about like how to match up all versions that are available versus what it knows works and stuff. And it try to solves for a solution to find like a matching set of stuff. And then it works hard to try to build a compatible set of stuff, but it can only operate on knowledge that is every time somebody makes a package and puts it in the repository, they have to declare what is, what works with it. And like for PySam, apparently it's not completely, somebody just did something like, oh, PySam, but they didn't say which PySams. And as PySam evolves, you get incompatibilities and then it breaks, but it's kind of it's really the package manager's fault. We have to do this right now, but it's not that uncommon to happen. I mean, like some packages that are heavily used will always be correct because like as soon as they break, somebody will fix them because it's like 100,000 people are using this package and it will be noticed immediately. Other packages, it's kind of slower, especially academic packages that just, once the developer gets it working on his own machine, he doesn't really care so much. So he's probably not installing it from scratch every time, or testing it in fresh environments. So anyway, it's just a fact of life these days with modern software universes. Right. So the alternative is okay. First of all, both of you I think are trying the vend method. Is it working for you? It's slow. Oh, it's like it hasn't even gotten to that thing. Oh, Python, it's building PySam. Yeah, that's the hard one. That's the one that requires the C compiler stuff.
Yeah.
And you two are also in the compiling PySam. Yeah. So PySam is one of the Python packages for manipulating BAM files. So bisulfite bolt needs to create BAM files, and it uses PySam to do that. PySam depends upon the same library that kind of SAM tools depends on it. So it's sort of like pulled in the C library for SAM tools, it's compiling that library and stuff like that. Anyway, there's a lot of work. If you do top or whatever, you'll see all kinds of processes are flying by on this node trying to satisfy your requirement there. But yeah, PySam takes a couple minutes to build. So and if PySam succeeds, it's highly likely that you're good. Unfortunately, you're probably going to have to compile PySam twice because, as I say, it's probably compiling 0.24.0. I don't know if you have enough text on your screen to tell what version it's trying to install. Might be up. Oh no, you're getting 0.23.0. Or is it that's the bad one? Oh, 22 is the one you need, right? Okay, yeah. So it's pulling in 23. But you're gonna have to downgrade to 22 and it's gonna have to compile again.
Okay.
It was fast for me because there is a global package cache that's in your local directories that's outside of the virtual environment because the package cache can be shared between virtual environments. So somewhere in your home directory, it's like, I forget, it's .local or something or whatever. There's somewhere in there, all the virtual environments are sharing the downloaded packages and the pre-compiled stuff and whatever. So the reason why it was fast for me is because I've already done it once. And outside of the virtual environment in my home directory somewhere, there's cache versions of all those compiled things. And so Mine was able to pull out the precompiled stuff it had already done a week ago, whereas you guys are having to do it from fresh. But if you guys were to do this twice, it should go faster because then it should have in your home directory is precompiled.
Mine is still done.
Okay. You're done, but okay, if it's done, you can try typing VS bolt and just hitting enter and seeing if it runs. But if you get an error message, then that's the PySam problem. So no, it's not working. And if you kind of see why, if you look deep in your PySam, you can kind of see it's like a PySam problem. So that kind of gives you the clue. It's like immersion mismatch with PySam. So now the way I figured it out is then I just look on the internet for all the PySam releases, find 23.0, and then look what are the version numbers going backwards in time. Then you just try them one at a time until you find the right one that's it is, and you have to. It's like 3 back right now, but it's so funny.
It doesn't give you any hint, though, right? You just have to do trial and error. Like here,
Yeah,
it doesn't give you any hint that
this is
because no, that's by some
you're
problem.
debugging somebody else's package at this point. So yeah, anyway. So run the second command that locks PySam to the correct version. That's the one you need to run. And after you run that one, which is going to be painful because you're going to have to recompile another version of PySam. But then your BiSoft is multiple. So are you? Okay, but you did try it. Oh, you did try it. You did try it, and you got the same message exactly. So, yeah. So like, I've been using BiSoft Bolt for years, right? And I've been doing workshops with it in various forms for years. And it's like every time I teach it, it's like it's changed again. Like, I mean, you have to kind of figure it out again. Like it used to almost work out of the box, right? Like you didn't have to load a GCC. You just do Python pip install done. But over time, it's sort of like, anyway. So this is highly reliable. This will get it work. So after you've done your downgrades to 0.22.0, then you should be able to say BS Bolt, and it should run, and you should get something like this. You should not get the error messages that you were getting that the both of you just got. So the next slide, which is Conda based version, is like if the Python virtual environment thing still doesn't work, you can try Conda. So Conda is Python has got many packagings and distributions. Okay, so the VM stuff is kind of one way to go. Conda is another distribution. Conda is more almost like a whole operating system, not just a Python thing. It's like it's a very heavyweight system. I mean, it has all kinds of packages in there that are not Python related to, and it almost is like a Linux distribution all by itself. So, that's one reason why I don't usually do it first choice, because it's so heavyweight. On the other hand, because it sort of has a more expansive view of dependencies, it's usually better about keeping things self-compatible, right? Like, you'll notice that in the Conda version, so if I do module, so don't do this because I think your VMs are going to work, so you don't have to do this, but this was the alternative. The module system has Conda, and if you were going to try the Conda version, I would recommend you actually just like quit out of your current session completely, re-log into a login node, get a new compute node thing, and start over, rather than trying to have like half the VM stuff done and then try Conda with extra module loads active. It's a bad idea. So if you were to try the Conda, try it in a fresh session. Conda, you'll need module load to get Conda, which is the package manager, if you like. That's the Conda command is the thing that we need there. The blue line here is the equivalent of the VM creation on the previous slide. So this Python 3 MVM, blah, 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 that line is equivalent to the first part of this. But actually, you can give the package, if you give packages to the end of the create command, it already does like the package install part there. It's like a combo. That line is like a combo of this line and the upgrade BS Bolt line here. The -Cs are channels. So these are, if you like, whole repositories. So like Conda Forge is the main Conda repository. And then BioConda is an overlay on that adds a lot of bioinformatics stuff into it. And then CP Feral is some dude, which happens to have the place where the BS Bolt package information is, because it's actually not in BioConda. So this is just some random dude that packaged up bisulfite bolt, or I don't know, maybe this is one of the authors, I don't know. And so we gotta tell Conda where to get the recipe for how you should install bisulfite bolt. So that's the CP Feral channel. But you'll notice that then I can just go directly to activate, and I don't have to play around with versions or anything or not, because somehow on Conda they're all right. Everything's correct out of the box. So anyway, but that's an alternative. If you're doing like if you get into AI and stuff or so on, I don't think I've ever gotten AI stuff to work like straight out of base Python. Like it's just too crazy. The dependencies are too crazy and they change like every 5 minutes. Conda seems to keep on top of it though. The AI stuff always seems to be working in Conda. So, anyway. But as I say, it's just sort of it's a heavyweight environment. It takes more disk space because it assumes less about the outside and tries to reproduce it all inside. And it's sort of more intrusive and just it's also more likely to interact with parts of Conda that aren't in the environment and so on. Anyway, so for various reasons, I don't do Conda as the first choice, but it's certainly a choice. And for certain projects, it's going to be your top choice. But anyway, these are two alternative methods of installing Python stuff. So did your PySam recompiles finish? Still building. Oh boy. Yeah, it almost makes me want to make sort of like a pre-compiled version that you guys can use, but I also kind of want to have you guys see how to install it from scratch. So yeah. And does it work? Oh, I don't like that sound. You just say by itself. But it doesn't know that doesn't.
Right.
It did not, since it's already there. The same error you get with the 23 though. Are there any differences that I think I have the exact list of versions I've got installed. So let's see. So the combo I had it was working. So it's bicep 160, numpy 202, and pip 2511, and PySam 020. Why do I have a 23 there? It should be 22. That's the wrong list. What have I got in my pip 2511, PySam 0220, setup tools 5600, and TQDM 467.1. They were, well, interesting. Almost the same error. It's another PySam. It's basically PySam is trying to pull in something that doesn't exist anymore or whatever. Once in a while these guys rearrange things and rename things and so on. So something it's looking for doesn't exist anymore. So I don't know. I could tell you to keep trying older PySams or something, but maybe Conda is the way to go. So that you, like I say, that I think you should start a new session for though.
Oh.
Yeah.
Should I stop this now?
Well, you're running an experiment. You're running an experiment that says whether with module load GCC, module load Python, and then module load Conda that stack up three of them. I might recommend for you then when you activate the session later, like in shell scripts, you're going to have to activate the session. You got to do this context as you have it right now. So you did a module load GCC, a module load Python, then a module load Conda, and so that's your stack right now. So you got to keep that the same. Maybe you can get away with not doing those first two, but that's an empirical test. But the more likely thing to work is you got to keep the module loads in the same way you got them right now. Yeah, Conda works hard. I mean, Conda is like, it's like dozens of C libraries it's considering and so on. I mean, it's just the number of files Conda is going to make is much bigger than Beam and so on. But I think they're all precompiled and downloadable. It's just that it's going to have to think pretty hard because it's done. There we go. There we go. And there's a newer Conda. That's okay. Oh, you have more channels too. You have an R channel. You must have used Conda before.
Yes, I have, and I've had.
Okay. You saw all those downloads. Those were all simultaneously downloads it was doing. Conda has decided like some set of 27 packages it needs to simultaneously do. That's the transaction. And then it tries to do things like all at once. So it doesn't like have to like do it in steps where things could go. It's like trying to swap out all kind of stuff like all at once. So it's basically done all of its homework now. Now it's actually trying made its plan.
For Conda, I don't need the GCC and.
No, and if you're, so that was her thing, is she had actually started the Conda stuff without a new session. And so I was just saying when it comes time when she's doing shell scripts and she needs to get back into the Conda, she should do the module load GCC, module load Python, then the module load Conda, just because that's the way she created the environment. And I'm not sure how much of the environment depends on that right now. But you went with a new session, I guess. Or, yeah. So for you, when you do activation of this Conda thing in your scripts, you will not have those module load GCC and module load Pythons because you're going to do your Conda just from a straight module load Conda.
So I don't need those.
You're not going to need them. Okay. All right. So while you guys are still working on your kind of let's let that go and talk about where we're going with this. The other programs we're not we'll see how far we get, but the other program we're going to need is SAM tools, because after we do the alignments, we're going to have to merge the BAM files and sort them, merge them, index them, and that's all SAM tool stuff. But that's in the module system already, so that's just going to be a module load SAM tools. And once you do that, you should be able to do SAM tools. So I've got it to the point where I can do BS Bolt and I can do SAM tools, and I'm good to go. Okay, so let's do one alignment of one part, just so that we can see that that's working and also get some idea on memory and time. So this is now a test run before we kick off a 42 part run. So we're going to have a shell variable that is the current file name we're working on. So this is one of the part files to do. So this is an example of one job that needs doing. And then this transformation is to compose the output file name automatically. So if I look at that, you'll see what that did. So we take the input file name, we truncate the .fastq.gz, and then we put this on. And here I'm putting in just some reminder to myself of sort of where these alignments came from. They're alignments from bisulfite bolt against the GRC H38 human genome release from Ensemble release 114. So this is just some rough parameters to help me remember what the details were about these alignments, because that's the program we're going to use, and this is the reference genome we're going to use. So you see here that this is the start of an output file name. The .bam isn't on here yet. That's okay, because actually the way bisulfite bolt wants the output name, it doesn't want it with the BAM on it yet. It just wants the unextension version of the name. So this is the kind of output file name that we're give as a command line argument to bisulfite bolt. Okay, so that's what that is. We're going to have to, bisulfite bolt can be, takes a thread parameter, so it's able to use multiple CPU cores. You just have to tell it how many to use. This shell variable will just keep track of the fact that our session right now is 3 cores, so we'll put that in a variable. And this is then going to be the alignment command. So if you do bisulfite bold align, it'll give you the help of what all the options are. We're going to leave most of the options at default. The only really critical options are the pre-index human genome, which you already copied on day one. That was in the directory as one of the files that I gave you because it's 18 gigabytes and it takes 3.5 hours to grind up the FASTA file you download from Ensemble into that. So that's done for you. But you have to tell bisulfite bold what is the database, as it calls it. That's just the directory where it can find the ground up human genome into the indexing format it likes. Bisulfite bold is based on the BWA aligner inside. So mostly what's inside this directory is a BWA index. So the F1 is where the first end of paired end reads go, and that is where we give it our FASTQGZ. These are single end reads. If there is paired end reads, bisulfite bold takes an F2 argument where you give it the name of the paired ends that go with that.
Like a separate index, or like I can use BWA index.
You don't want to mess with this directory. This is private to bisulfite bold because it's pre-processed the genome. Because the alignments have to be done in a certain way for bisulfite alignment to allow the C to T ambiguity. And this is all in there. This index isn't for you to touch. But if you just want to appreciate what's inside of it, it's basically the genome's been processed by bisulfite bold a bit, and then the BWA aligner, a modified version of the BWA aligner has index. You would have to create it. So that was actually at the bottom of, I didn't go over it, but when we, on these slides, this is the bottom left corner here is talking about the reference genome. This is the link where you can get the reference genome. This is the index command that you would run to create the index, but it takes 3.25 hours. So we're not doing that live. So
just a question, like this is for human, but
this is for
mouse.
Well, then you need to find the mouse genome. And there's not just one, it's which version of the mouse genome do you want? So, right, but basically you need to find the reference genome that you want to use and then index it. I did check with the Conda version and with the VN version that they produce literally the byte identical outputs for the index. The index can be shared between both of these versions. So it's not like the index, there needs to be a VN index and a Conda index. It's the same index. So I only gave you one copy. Oh, the Conda works. Yeah, well, that's par for the course, really. That's good news, but you can see it's more aggressive about sort of
Like all the-
building its own universe.
Yeah, this one is 0.1.
Okay, whatever. Not gonna. You're getting close though. You're almost at the end. Okay. Then the -O is the output base name. That's the thing we just did here. And then the last argument that's really relevant for us is -T, which is how many CPU cores you want bisulfite bold to use, mostly in that BWA alignment stage. So this is what our command line is. We could run that by itself. However, you can put this on the front, and that's helpful because that's going to give us a whole bunch of statistics. So user bin time and the -V asks for like lots of statistics. And then you can, so really the program we're running is time. Time is going to kick off bisulfite bold in a very similar way as a shell would, okay? But kind of like we saw with xargs, it's kind of like options to time versus the template, the kind of the program you want it to run, the command line you want it to run. And the double dash is sort of the break between those two sides. So this is the time part and time parameters. This is the command line you want time to run on your behalf, okay? And so time will essentially create a little shell, kick off this command, but it's collecting statistics the whole time. And after the program is done running, it will emit all these statistics, which will be helpful for us. We'll see that in a second. So I think that one part takes about 5 minutes to run. So let me get this running. Okay. No, that's not good. I must have missed a shell variable or something, right? So one thing you can always do if you've got a command that's being ornery, just put an echo on the front, and then you'll see what all the shell expansions have done to it. So that looks kind of okay to me. line dash v bsbol to line db. This should exist. Yeah, that exists. It's got all kinds of stuff in it. That's fine. This file should exist. Yeah, it does. And then this shouldn't exist. Oh, wait, that's not right. That's got like some of the, no, that's okay. That's okay. Unless does anything with that already exist yet? Empty BAM. Well, maybe I need to do conda as well. Oh, here's the problem. I'm just got unlucky on the node. Our memory requirements in this node are a little shy. I now remember why. I think actually, yeah. All right, so this worked on Monday as is, but today, for whatever reason, on this particular node, we need a little more memory than our, what, 3 times 4, 12 gig of RAM or whatever we've got in this current session. So you see up here, where was it? Cannot allocate memory, right? So, and it's from BWA. It's a message from the BWA aligner that bsbolt kicks off internal to it. So here's the command line to BWA that bsbolt is trying to run, and then BWA is running, but cannot access. This is a memory problem. We're too short. We need more memory. So exit the session. Or oh, I know what the problem is. This was the wrong window. This was my temporary, in quotes, window that I left on a login node. I wasn't even QRSH anywhere. This is the window I'm supposed to be doing my work in. So that is whatever resource limits I have on a login node, which are small. So that was my mistake. I don't know why this window seems to be frozen, actually. I'm hitting return and getting no response from this, and we haven't been using this window for quite a while. So I am going to quit that. I need to get on a compute node with reasonable resources, because that was a problem of me not of being on a really memory restricted node. So where's the stuff here? Oops. Okay. And your conda should be done by now. Oh gosh. I do have to say Hoffman feels a little slower. Like Monday was better than this. It was like, wasn't this bad.
Yeah, I've noticed that Kaufman sometimes gets just very slow.
Yeah, I think so. One of the big bottlenecks on Hoffman is the network storage, because all nodes, we're all hitting some, I think it's like 8 petabytes or something, but we're all hitting this fancy magic box, which has got all the storage for everybody. And that is a network file system that is in simultaneous use by the entire cluster. So that has to be a very high performance file. That has to be a very high performance file server. And it is, but I do think it's sort of one of the weaker spots. So if a lot of people are doing a lot of IO heavy stuff, that can bog down. And everything we do involves files. So even for the shell to sort of like give you a shell prompt, like one of the things the shell has to do is like figure out whether there's any new commands that have been added in your path or not. Like if new files show up in user, in one of those directories, the shell has to know about it. So like the shell is always kind of poking at the file system, even just if you're not running commands that are really heavy or whatever. So even just to kind of give you shell prompts, there's already sort of like interaction with the file system and stuff. And so, yeah, I think sometimes, some days, if there's like 1,000 heavy IO jobs running on the cluster, all of the IO gets slower, and you notice that even in the interactive bash and stuff like that. So yeah, I think there are days when it feels slow because
Yeah,
because it is slow. Oh, great. So Conda is the way to go for you guys. Maybe the next version of this, I'll just make Conda the first choice instead of the VMs. Okay, I am back on a node with reasonable resources. I have to reactivate my environment though. I don't have to recreate my VM. I'm in VM world, or maybe I should do Conda like you guys, but I want to. It's already almost 3:30, so let me just activate the environment I already have. So how do I do that? That's the yellow lines, right? I do not do the blue lines, which are for creation and install, or and configuration of the environment. I just have to do the lines that get me back the way they were. So these are the things I had already loaded before I even did the environment. So these are kind of dependencies of the environment. And then this, I have to do the activation again. So now I'm back in my environment. Okay. And BS Bolt should work. Great. Yeah, anytime. Anytime. Oh yeah, file system feels slow today. Okay, so good. We're ready to run it, right? So that was here. These shell variables would have been lost, so I got to reestablish those. Okay. Okay. And we're ready to run this here. And this should work this time. Okay. All right. I do have. All right. I will make this one a smaller font or something just to remind me this is not the primary one. But let me get just another session so I can just point at files in here. We can see them. So there we go. There we see a BAM output file for the first guy, but it's empty yet because things are working. Okay. So I could have put this user bin time in the background, and then we could have done like top or PS inside the right node. It's node 7165, but I could directly do an I'll do this. I'll just do a quick temporary SSH just for a process listing, just to see what's running on 7165, which is where my main session landed. Oh, this is brutally slow. You know, there was a few, I don't know how long you've been using Hoffman, but kind of last quarter or something, there was like even like a half day when sort of like the file system was completely jammed. And like all jobs were hung, like all interactive sessions were hung, all jobs and projects were hung. And it was like, they actually recovered okay, but it was basically like the file server stopped surfacing requests. And when that happens, all the nodes with IO in progress just have to wait, right? It's sort of like, it's like processes trying to read from a file or write from a file, and the other side isn't answering. The default behavior is to hang forever until the other side responds. So it took them like 12 hours to get the file server back in shape or something. And when it came back, everything was fine. But if you were trying to work during that 12-hour period, then it wasn't very fun. And it was kind of confusing what was going on because it's like nothing happened. Oh, there we go. So there you see, you see some progress messages from BWA. And this was the process listing on that node. And you see two SSHs because one of them is the session here and one of them is the temporary SSH to do this PS. You see the bash there, which is the bash down here. You see the user bin time, which is the command that's actually running. But then you also see, you should see a Python that's doing bisulfite bolt. Yeah, so like this is the invocation of Python that's running bisulfite bolt, the actual Python code. And then somewhere in here, you should also see like the BWA that's running. Yeah, here's the BWA that's running. So it's a very long path, but this is actually the path to the executable, right? So this is an absolute path to the executable, which is inside the virtual environment, right? So for me, it's the VM version. This is the directory of the VM, and then somewhere deep inside there is a BWA executable, and then this is the command line options to that, and that's the BWA that's running, which is the thing doing the heavy lifting and the main thing sucking up, time and memory right now. And what else is running? Oh, and then there's a stream BAM running. This is the part bisulfite bolt looks like it's kicked off another process whose job is just to sort of receive probably like SAM uncompressed output and turn it into compressed BAM output. It's like almost like we use gzip as a filter to do streaming compression or decompression. This is probably basically a streaming BAM compression. Okay, it's done, I think. It's almost done if it isn't literally done. Oh no, it's just batches. So BWA does like the file in batches. So that was what, a 300,000 read chunk almost. Well, our file's 500,000 reads. So probably one more chunk, and this chunk took 244 seconds or 81 real seconds, 80 real seconds. So anyway, we're probably a minute away. Oh, you got an error even in Conda? Broken dependencies. That's the wrong version of BWA.
BWA?
Yeah, yeah. So this BWA that it's built. Oh, now here's my question though: is this could be your module loads stuff? So you remember because you didn't do a fresh session. You didn't do a fresh. You remember you didn't do a fresh thing. So maybe we need to unload. I mean, and we're really just doing things the wrong order now. Let's try removing the GCC, because this is really, that's a C library version mismatch. That's what this is. This BWA was compiled against a GCC that's a different version than your C libraries are right now. So maybe that's interacting with this thing and you know, when I have you do Conda, it isn't there. Let's see if that fixes it. No.
Should I use?
This may just be try a fresh session. Try a fresh session. Without the extra module loads in there. My guess is that your VS Bolt works because that is Python only, and that is a problem with BWA. The compile message doesn't require it. So that's why this works, but when you actually try to do anything, it doesn't work because it's BWA is the problem. And it's a version mismatch between the C libraries that are active right now and the C libraries that this thing was compiled with. That's all Conda's stuff. I mean, Conda should have taken care of that, get it all consistent and right, but it's possibly because you created the environment while you had this GCC activated. So my recommendation would be to make a new session. Don't do those module loads from the VM. Do the Conda. Let's move this Conda aside first. Make a new session, remake the Conda environment without the module of GCC humble and hopefully that'll work. This is really making me want to kind of create a pre-compiled FlexLocal bolt because this is really turning into quite a battle. This is supposed to be pretty smooth. The VM is supposed to make it pretty smooth, but you are also having issues. Oh gosh. All right, I don't know what to tell you because this guy did the fresh session for Conda and he's got the same problem. So that may not work. Yeah, it's a BWA problem, but now it's no longer a PySam problem. It's now a BWA problem, and it's some mismatch between the C libraries BWA was compiled with and the C libraries that are active on the system. So one of the things Conda is supposed to take care of is sort of like make such a complete universe that that's all not really an issue. What a nightmare here. And this is the first time that the VM and Conda tricks didn't solve the problem like immediately. Like, okay. Can you guys use my virtual environment? Let's see if that works. So let's see if that works. So I need to make this be readable to you because right now it's not. So the permissions, oh, even the permissions deeper down don't have all the permission bits. Good. Okay. Let me try this. Okay. Okay, so deactivate. No. RW2. I think it's 022, the UMask I want. Okay, now when files get created for me by default, everybody can read them. That you can't write them, but I can write them. I can read them, but my group can read them and you can read them. Anybody can read them. So when I create the virtual environment now, maybe all the files in the virtual environment will get permissions such that you'll be able to see them. So now I should create the virtual environment again. But this will now create a virtual environment that's readable. And then maybe you can activate my copy of the virtual environment and you'll be good. So let's give that a try because mine is working. So I need to create the virtual environment. Those module loads are already done for me. They're already here. So I need to do the blue stuff again. Shouldn't take long because everything's already compiled for me. Yeah, maybe the next version of this workshop, I need to choose a program that's not so ornery to get installed as a demo.
The GCC version when you make the template.
You can, but you really don't, you kind of don't want to go down that rabbit hole. Like, I mean, kind of supposed to make your life easy, not like cause you to have to debug a whole nother system. So, oh, no, okay, I didn't do the activation yet. Ah, crap, that's actually doing my global Python, not I forgot the activation line. Okay, so there we go. The bisulfite workshop W6 was just taught last week. I don't know what he was doing for the bisulfite. He used bisulfite bullet. I don't know what he was doing to get it installed for people. And I tried everything Monday and everything worked. Both of V and Van Conda worked on Monday. Let's see if it works before I do the downgrade. No, it doesn't work. Okay, that is working. Now, is that virtual environment, all the files marked readable to you guys? Let's find out. That looks pretty good. Yeah, they do look all readable to you. Okay, so let's have you guys try to use mine. So how would this look? So I'll do it from from a new session, right? So when there's a new window, just like you guys. Okay, so your shell prompt is like Hoffman normal. You don't have any you don't have any. I got to keep digging out this resource requirements. Okay. Okay, and then back down here. Okay. Give me a second to get on a compute node. All right, we're going to do an experiment. I never had the attendees try to use my own copy of the virtual environment. If this works, actually, it's a good solution because it means I'll just make the environment work and then have you guys use it directly. And we don't have to do any of the install of your own stuff. And because that's always seems to be fraught with difficulties. So, okay, so I'm now where you are. So first of all, your prompts look like this and don't have the conda thing or the VM thing. You're no longer in your environment. Okay, so if you are in one of those, the way you do it is if you're in VM, you say deactivate, and that goes back to pre-activate. If conda, I think makes you say conda deactivate is the way to get out of it. But anyway, that's how you undo the activation anyway. So now you're back to normal. Now you need to get your module, say module list, and you need to get exactly these two in your list, right? Because you're going to use my VN, which is built off these things. So you need to get your module list to look like this. This IDRI and Intel stuff is always kind of on, that's the Hoffman defaults. But basically, you should then see this GCC and this Python and nothing else. Okay. So if you're too short, you do the module loads to add things. If you have extra stuff in there, do module unload to unload things. So get it to the point where you just got these two. Okay. Is that's true for you, or?
It's a parallelization.
You got to unload the mini fortune, or you can do a new session. I mean, you can do that too. But you should try it's module on. Then you got to get the name. And I don't know what the version of is required. You get the name of the thing you want to upload, and I'm not sure that the order might matter too. I don't know. It's I don't know if conda depends on mini forge or mini forge depends on conda. But I might suggest you actually do them right to left because this is probably the order they came in. Okay. You can do one at a time. You can see if it works. Oh, it can unload it many forge for you. You can also kill the 2715 by because that's not the right guy. And then how okay. Yeah, you look good. Okay, so all right. So then you're going to try to activate, you're ready to do the activation line, but now you need to do the activation line in my place. You're going to call the script from my place, right? So instead of saying use scratch, that's not where you're going to want to get it from. You want to get it from use scratch C focus. Okay. So this is looking good. I mean, this looks like it actually has a chance of working, and maybe this should become my preferred method of doing it. You know, we're like more than half an hour on this install part. It's crazy. So that did not work for you.
Do I need to load the?
Oh, you don't have the two loads. You undid this. You got rid of the extra stuff, but you haven't put the missing stuff yet.
The GCC one.
Yep.
This is working.
Oh, well, there you go. Okay. So that works. Okay, so I can make a environment that you guys can use, and that will become the new solution because I did not expect to have to spend this much time. Anyway. I wish it worked because then you would have had the ability to feel like you can install random stuff on your own too and so on. But this is a little bit also kind of like what like modern software packagers are kind of like. It's kind of like you blink and the internet's changed on you, and now things that used to work don't. And anyway, so sorry, anyway, it's it's a different kind of lesson is all is the way it came out, but your user bin time is working. So this works great, and you're about to see your user bin time working, I'm pretty sure.
That makes me feel better because I spent days just.
Yeah, it's working now.
Well, try the user bin time, because you need to see if the BWA is working, and not just it starts with a leading slash. You've got a leading slash. It's an absolute. It's on the slide. You want to get from it's pretty long command. You want to get from the slide. Or from the copy and paste file, whichever way you like to.
This one, yeah. We should put working on just
You seem to have been having pretty good success directly copy and pasting out of the slides, which not everybody does. But that's why I give the text file in case that's problematic. But. Oh no! How can you two be different?
Is it the command copy okay? Because that was the one command that didn't copy okay. I had to like put it.
Oh, cannot allocate memory. Where are you? Are you in the login node? What node are you on? Oh, you're in 6017. How much rent? How much? What are the resources in this environment?
I guess
It's those. That should be enough. I can't believe it. You've got the memory problem. So cursor would go to be on. You're not on the login nodes. That's good. It's a little hard to tell. Five spots. So that does suggest you are running under those resource requirements. But then why do you get an out of memory error? Which you should have plenty. You have the 800 seconds you got running now.
I just want.
Why don't we start another session? Let's take you down to 3 cores, but increase the RAM number. Let's just for. Oh, you can't. Yeah, it's a slide. You can't change it, right? Give it text editor. Let's change the 5 to 3. So what is 5 times 4 is 12? 5, 3. And let's go do like 27 times 8 times 3 would be 24. Let's try 8.
You already come to us. Let's go but more.
Yeah, let's just try that.
Inside more core.
I believe that should be forced to remove. Two module loads, deactivate, and then try the time. So both of you have now solved the problem of the install. I mean, both of you are now successfully using my virtual environment. But your problem right now is a resource, it's a memory problem, which is no longer an installation. You are running by solvable, okay, NBWO, okay. It's now a different kind of problem. Module load GCC, the module load Python. 11.3.0. Have completion been it's smartness actually, even though it's on 3.9. And then the source of the bin activate inside my directory. You don't have a shell variable. These shell variables. That's the line. So your one probably finished,
Yep,
and you got all kinds of stats out.
yes.
Yeah. Great. No, it's day one. Slide.
That's going to be here.
This delay in BWA is reading in the roughly 12 gigs of index into RAM. Probably in two 6 gig pieces. So last time you got like a 6 gig memory allocation error, probably going to try to do the second piece or something. IPO. Longer than it did last time. I think you're okay. Because I think it's read the index, it can move on to working and reads now. The memory usage of BS12 is essentially constant because it's all based on basically the index. The index is the thing that has to keep in memory. The reads it does in tiny pieces, little chunks, and the size of the input file doesn't really matter much. So if it survives to the point where it gets the index in memory, you're good. And you are good. Yeah. Fine. Okay. Well, that. All right. So this is the stats you get kind of out. And two things. First of all, it worked eventually. We finally got it to work, which is a requirement before we can run many pieces. We got to get one piece to work. So if we look, we got a BAM file and it's got like a size. And like if we like I think I lost my module load samtools, but if you do samtools view on that BAM file and pipe it to less, it's got alignments in it. It looks good. And I don't think I saw any error messages when we ran the thing. I think I've scrolled off. I just scrolled off my stats though. So anyway, that was a bad idea. But the slide has a capture of what the stats look like. So the output has two parts. This is the output that came out of bisulfite bolt itself. You see that there is some progress information and internal kind of messages from BWA and stuff. But at the end, bisulfite bolt, the Python part gives you some alignment statistics. Like it says, like alignment 4.5 minutes. There were 500,000 reads. They were 93% mappable, 7% didn't map, roughly half to each strand, plus and minus strand of the reference genome. 30,000 were unmapped, and 34,000 mapped to multiple places, and I can't tell where they go. So, but that looks roughly fine. That all looks right range. The next part of the output comes from the user bin time and is statistics related to the resources used to complete that command and all of its subchildren, like the BWA is included and stuff. So the entire whatever got, the whole universe of computing that happened as a result of this command has been included in these statistics. So some numbers here that are important. Well, first of all, it tells you the exit status is 0. So the bisulfite bolt declared itself a successful run. You see maximum resident set size in kilobytes. And so if you imagine kilobytes, if you imagine 3 more zeros there, that's actually bytes then with the K. Maybe it should be times 1024, but let's not worry about that level of precision. That's 13 gig. So the peak RAM usage that this thing had during this run was 13 gig. That tells you that's very useful information for sizing this job, because all you know is that the total amount of RAM in your session is probably enough because it did work, but that doesn't necessarily relate. We could have given our session 50 gig of RAM. Also, we then know it's less than or equal to 50, but this tells you the actual peak was 13 G and change. So that actually helps us plan more runs. It was 4 minutes, 55 seconds wall clock time, and the average CPU usage was 138%. What does that mean? On average, 1.38 cores were busy. We told it to use 3, but it only got 1.38 out. That's a little, in a way that's sad. It should, it'd be nicer if that was 3. Well, that means either one of several things. It could mean that the way bisulfite bolt or the BWA process that does the main lifting inside of it works is that they aren't perfectly parallelizable or something. There's some deficiency in the code that makes it so that they can't really make use of all those cores. That's actually kind of unlikely at the moment. But here's another possibility, which is probably the more likely one right now, which is BWA has a big startup cost. It has to read the entire genome index into memory before it can go. And that's, like, some of you have seen when you ran it, there's that part where BWA says the command line that it's running BWA. But then there's kind of a long pause before you actually start to see BWA is reading reads and doing stuff. That long pause, if you actually look with top and stuff, you'll see that the memory is increasing, and it's basically reading in those big index files in that directory, that database DB directory. So that is a part that's single threaded and IO bound, and we're only burning through probably a fraction of one core at that point. We're not even probably using 100% of a core, because that's essentially waiting for the network disk to kind of send over that 12 gigs of memory, a file that has to come over. So if the total length of the time spent to align the reads is very short, that means that most of the time we were kind of in this IO limited kind of startup time, and that's all almost 0 cores of usage. And then maybe our actual alignments were really using 3 cores. But if you average these together, and this was a minute, and then, or a minute and a half or 2 minutes, and then this was only a minute or something, you're averaging a 0 with a 3. And if they're roughly equal time, that would be 1.5. And so this number may not be that accurate for a run this short, right? So this was 5 minutes, of which maybe 2 minutes was spent reading in the index. So that could be why this number looks so small. And so actually, before you sort of conclude that it's not even useful to give bsbolt 3 cores or whatever, you need to do a bigger run than this because of that startup stage with BWA. So as we go on, we'll actually give it 3 cores or more or something, and we'll see later runs do a little better. So it is some kind of it's probably the startup thing that's the business. It also says that probably 13 gig of RAM, that's too small. You want to give some margin there. Maybe that means we try 14, 15, 20, something like this or whatever. But you now know, if you were running this program for the first time and had absolutely no idea how much memory it reads, you may have done an interactive session with a big resources. And then you would run it this one time, and then you would get the stats here, and now you would actually know kind of what the order of magnitude more is, right? So maybe, oh, this is a new program, it's a bioinformatics program, it could need a lot of RAM, I'll give it 50 gigs to start. But then you start running your pieces and get the stats, and you're like, oh, but it really only needs like 14. So then that tells you, that's good advice to know when it comes to actually composing your resource requirements for the large list of jobs, because you can now dial down the 50 down to something more like 20, and that's going to give you a better chance of getting more jobs running at once, and less wait time to get those jobs kicked off than if you did them all with the 50 that your large interactive session was. So that's what the purpose of this is doing. So this is to verify that our command line is correct, the software is installed properly, and get the resource idea what a typical resource needs are for a part. Okay, so now we are on the day 2 slides or part 2 slides. Anyway, yeah, so that was a big chunk of time trying to get that software worked. And now that we know that you guys can use the virtual environment in MySpace, that will become the preferred way to do this in future, because then we can skip all that time trying to get it working on your side. Okay, so we don't have to do this because so if this really was the start of a new day, the first thing to do on that day would be to get you back in the environment, right? So that's why we've got to do the module loads and the activate and stuff like that, but you've all got a functioning environment right now. So we don't have to touch that. We don't have to worry about that. This is just repeating the statistics. And this is the discussion we just had about like, oh, we didn't do the time. We did the 138% CPU usage and the peak RAM usage discussion. We haven't done the time discussion yet. So the running time was 5 minutes, but I kind of told you on day one that sort of like a good time to target for Hoffman is under 2 hours, because that's sort of like very easy for the scheduler to place into like holes in the schedule. Like somebody's got a big resource requirement. I need 30 cores and 200 gigs of RAM. Well, that's most of a node. A lot of nodes don't even qualify, and that's most of a bigger node anyway. So the only way the scheduler can meet that requirement is it's almost got to empty out a node. It's got to empty out one of the bigger nodes for that. Well, jobs are going to be running all over jobs are going to have all kinds of deadlines at the moment. And so you're going to have to wait for all those deadlines to drop off. So in a way, the scheduler now has a hole. The scheduler now knows at like 6 p.m. when all those jobs are finally going to finish and the node's going to be empty, he's going to be able to start this big job. And so he's kind of got, a mental block diagram in his mind's eye, right? He's kind of got like all these current guys that are running right now. And then he's got this line here where he's planning out this guy here. But that kind of creates all these holes here where maybe not all the cores and all the RAM are in use, but until I have a job that fits in those holes, I can't place them. But by making your jobs short time, short, low cores, and low RAM, it's easier for the scheduler to fill in those holes. And now you can use parts of the schedule that other people can't. And that's how you can get lots running and not much waiting time. So 5 minutes is too short though, because for example, we talked about how BWA has this big startup phase where it's got to spend like 2-3 minutes reading in the index and not making progress there. So if your total run is 5 minutes, half the time it's spent doing like work that's not productive for that actual part. It would be better if your parts were more like half an hour long, right? Because then the 2-3 minutes at the beginning is not much time compared to the 25 minutes or 27 minutes that is actually spent doing useful work. So 5 minutes is too short of a part size, because there's overhead per job and it can be substantial. So, you may say, like, well, why not target like an hour or something, right? Well, as I said, 2 hours is going to be our job deadline. Like when we request the jobs, we're going to ask for 2 hours. And that's a hard limit. If we go over that, the job dies, and then we'll be in a situation of having to figure out which parts failed from that and rerun them. So we don't want to go over the 2 hour limit. If we targeted 1 hour, then the problem is that there's so much variation from job to job, because some nodes are faster than others, because not all the nodes were bought at the same time. They're different hardware. Some nodes are overloaded because people might be using more RAM than they really asked for, or more cores than they asked for. And so you may be making slower progress than you might expect, all other things being equal. So there's variation in the hardware, there's variation in what's happening in terms of what's running at the moment. So if that variation is 2 to 1 or something, and you aim for an hour, it's just sort of like too close, where it's like too likely that you're going to go over 2 hours on the slow parts. So maybe aim more like for half hour, because a half hour is long enough that you don't have the overhead. The overhead per part isn't so bad. But even if you multiply by 4, you're still under the 2-hour time limit. So it's kind of the right range to target. So no matter what you're doing, I sort of recommend you try to get the parts to like the half-hour size as your target. And for example, in this case, we don't really have a lot of flexibility with RAM. The way bisulfite bolt is written, BW is written, it's got to have that index in RAM that takes a certain size depending on the size of the genome. It doesn't really take a different amount of RAM depending on how many reads you're going to pump through it or how many cores are working on those reads. It's all about that index. And it's sort of like for a given genome, the memory usage of bisulfite bolt is almost a constant. And so we don't really have control over it. We can use the stats to figure out what that number is, and we'll aim a little higher than that because same reason, you don't want to cut anything too close. You always want to give a little bit of margin. So maybe we'll round it to 15 or something, or 20. But that's not really a number that, for this particular application, it's not a number that depends upon the particulars of the input. It's completely insensitive to the size of the input. So that's how bisulfite bolt resource sizing kind of goes. So these 3 slides are just sort of just repeat that discussion for reference and so on. So this is basically just the discussion of sort of like how you take the test run information and these considerations that we just talked about to determine the resource requirements that you're going to do when you start doing the parts. Okay, so that's basically how you match that up. So but there's one more thing to talk about though before you start running parts, and that is you should also check disk space, because that's not really a resource requirement that you talk to the scheduler about, but it's certainly important, and going over quota is going to give you a bad day too. So it's worth it spending a few minutes to think about just, oh, how much disk space am I going to need for these 42 parts to succeed? So we've done a test run, we can kind of estimate that just on the assumption that all parts are going to have a similar behavior. But one thing we can do is we can look at the size of the input file we did for this part. This input file is this many bytes long, 45. Not sure why it's different size. Maybe we did gzip fast and this was a gzip best or something, but it doesn't really matter, not for this level of precision that we're doing for this rough estimate. But basically, here's the byte size of the input. This is the output file. How big is that? Oh, there we go. That's this. Okay, it's actually a little bigger than the input, because BAM files contain actually all the reads inside of them anyway, plus the alignment information. So they do tend to get bigger. So I'm going to divide those. So roughly, it's a 1.5-fold increase. The size of the BAM output files are going to be roughly 1.5 times the size of the inputs. And we know the total size of the inputs. We can ask DU to tell me all those SRX part files, how big are they in total? About 1.7 gig, because this is the cut down stuff we were doing just the head, remember? So that means we can already estimate the disk usage required for the full thing. 1.7 times 1.5, 2.5 gig we're roughly expecting to create in new BAM files during the run of this operation. And then we say, oh, but I have like 2 terabytes. So, and I don't know how much I'm using right at this moment. You could use the quota command from yesterday to do that. I don't have to worry about this anymore right now because it's not a big deal. But if you were doing the full size files, like I think the slide probably multiplies out, like remember the original inputs were 40 times bigger than these head cuts that we got right now. And what if you were doing 20 samples and not 2, right? So then it would be times 40 times 10. That would be 400 times bigger than what we're doing right now. So now the inputs is more like 680 gig, and the outputs are now more like a terabyte. And together, that's like 1.7 terabytes. And now you're getting kind of close to the 2T. And now it might even start to depend upon like how accurate our estimates are. And even if that wasn't over, we're going to have to do one more step after we BAM align the parts. If we align the parts, remember, then we have to merge them back into the 2 samples. That's going to require another copy, right? And depending on how we do that, like maybe we do one sample and get its output and then delete all of his intermediate parts, we could save a little disk space doing that or whatever. But depending on how we do that, if we just did it without deleting anything, we're probably going to create like another terabyte because that's another copy of all the BAMs basically, right? And so now that's 3 terabytes and now that's over 2. That's definitely over 2. So then maybe you do have to do it one sample at a time, 10 samples at a time or something, because now, anyway, this is the utility of having to do the disk space estimation, right? Because you're going to save yourself from getting in the middle. If you just try to do it in the 3 terabyte way and you get in the middle and you run out of disk space, well, now you've got a mess, right? Because you're going to have to figure out which guys are complete, which guys aren't. You're going to have to delete the partial things, probably copy off this stuff. You're going to have a whole bunch of stuff happen that's kind of painful to recover from without losing some of the progress that you did. So simpler to just think about it from the start, realize how many samples are you going to be able to do at once given your space requirements, and then you're going to have to do the game of rclone or whatever, moving storage in and out of Hoffman, and do amount of work that makes sense given the amount of quota you have to do it in. Okay, so there we go. Okay, so so we are now ready to take the next step, which is instead of running the bisulfite bolt alignment command directly in our interactive session, we're going to run it as a Q sub job. Once we get one Q sub job running, then we'll be able to run 42 Q sub jobs, no problem. But the next step is to transition into, we got to get our bisulfite bolt command into a shell script so that then we can have Q sub kick off the shell script. And we would like to parameterize that shell script in such a way that it's easy for us to use the same script for all 42 parts and not have to have 42 different scripts to do it in. So that's what this slide is for. This is the script. This is running the script as a job. So let's look at the script itself. You do have the script already in your directory because maybe you don't, because now we're on the day 2 stuff. So, okay, so you need to merge into your copy of the files the day 2 editions. So actually on slide 2 of this day 2, part 2's batch, there's this copy command. Okay, so go to your scratch space and go, then this is the place where you have like your W1c directory is the next level down. And then run this copy command. So you are now going to copy out of my workspace 1c place, not day 1 start, which is the big thing you copied yesterday, but now you're going to do the day 2 additions. And you want to merge everything in day 2 additions into W1c. So the way we'll do it is day 2 additions /star. That's all the files that are actually inside the additions and not the additions directory itself. So that's a whole bunch of files that are going to come along with that. And then we're going to dump those files into W1c. If you didn't have the /star, you're going to get a day 2 adds directory inside W1c, and that's not what I want. I want to actually merge those 2 directories here, which is why we do it this way. Okay, so if we do this, so let me just check I'm in the right place. Yes, okay, so there we go. And this is fairly small. This is relative to yesterday. This is probably like 5 gigs or 8 gigs or something, but it's not the 100 gigs that we did on day 1. So this should only take like 1 minute and not a lot of time.
/star will actually happen to you.
Well, the CP doesn't know anything about that star. The star is a shell thing. So what the shell will do, will go into this directory, and then find all the files in that directory. And then this will turn into like dozens of command line arguments to CP. It'll be the file names of all the things at the top level of that directory. And then the way CP works is you don't just have to do from to. The last argument is the destination, but you don't just have to give a single from. You can have from 1, from 2, from 3, from 4, from 5, to. And CP will copy all the froms into 2. If 2 is a file, that doesn't work because how do you copy multiple files into one file? Like, I don't know, I guess you concatenate or something, but CP doesn't do that. If you just do CP A, B, the A and B can be files, or the A can be a file and the B can be a directory, in which case it puts the A into B. If you do CP with multiple froms, the 2 must be a directory. And then it puts the files, all those files in that directory. So this is why this kind of looks like it's only 2 arguments, like A and B, but it's not. It's really, this is like many, many this shell will expand that into many, many files. And then this is a CP, many, many things to a single destination. The destination is a directory here, and it just dumps them. I don't know. Yeah, does that help? I guess. If you experiment and you do it without the star, you'll find out that you're going to get a W1c/day2 adds directory, a single addition to W1c, which is not what we want here. I want to have everything in that day2 adds just directly show up in W1c. I don't want the extra subdirectory. The reason why it's so many files is because I actually give you pre-calculated versions of all the outputs already in case we don't have time to do them live. So we will kick off jobs live, but we may not have time to wait for all the little live jobs to finish. So we will have, oh, it's done. Okay, so we will have, so now if I go inside W1c, you will see we have new files in here that we didn't have before. So you'll see that there's like this shell script here. There is all these directories here. So like these directories didn't exist before. But the tree did, but these guys didn't exist before. And this didn't exist either. So like these are additions, and this is an addition. And that's what the copy command just did. And then these things down here have more stuff inside of them. So there's this is where all the file count came from, is that a lot of those have a large number of files in them. So okay, so when you do that, then you will have a copy of the shell script. So here we are, and now you have a copy of this shell script already in there. That's part of what the copy just did, is give you this shell script. So let's explain this shell script here. I think it's colorized a little bit nicer on the slide, so we'll do it from the slide. So, I presume you've seen shell scripts before, because that's probably an intermediate. That's in the W1b, we cover that and so on. So, scripts start with a shebang line, this hash exclamation point, and then the name of the interpreter, which here has been bash. This is a bash shell script. We usually put in some echoes. These just serve as progress information. So like, sort of like logging. So like this will echo out the date and the node name that this script got put on. The $@ is actually all the command line arguments to the script will show up here. So we're kind of logging just sort of the situation that this script started in. That's not necessary, but that'll be helpful when it comes to looking at lots of jobs and deciding whether that'll help us with did they succeed or not. The shell script, as I said, we want to parameterize so that it's not specific to a part. It'll work for any parts. So the way we do that is that we let it take two command line arguments, one of which is going to be the number of cores that bisulfite bolt should use, because it's hard for the script to discover that cell that any other way. That's really something that we tell qsub how many cores we want to use. But then we sort of also need to tell this script, because this script has to pass -t number of cores into bisulfite bolt. And so the easiest way to do that is just to make that be a parameter to the script, so that we can arrange for that to get into this. We could put the number in two places, like in the qsub place, we could put that number, and we could hard code that number into here, but that's not a good idea. It's better for the script to not have to need any changes if we change the number of cores. And the way we handle that, we just arrange that to be the first command line argument to this. It's just the number of cores that the bisulfite bolt should be told to use. The second command line argument, we will just make be the input file name. Right? That way the script can work. We just keep changing the second argument. It will work with all parts. We don't have to specialize the script to a particular part. So those are the two command line arguments that it uses. The $(1) and the $(2) will expand into the first and second argument. We could make a third argument be the output file name, but we can actually build the output file name from the input file name. Okay. So these two lines build the output file name from the input file name. And some of this you've seen before, like the delete the fastqgz suffix and then change the suffix. You haven't seen this base name stuff before. And base name is just a utility that removes the directory part of things. So if you have something in a bunch of directories, it removes the directories from the name. Why might you want to do that? Well, that's because I've written the script to be quite flexible. I want this script to be able to be started with the current working directory, the CD, the PWD, to be anything. And furthermore, I want the input and the output files to not necessarily be in the same place or in the current directory. So I want the input file to be anywhere. And the way that will happen is that the person using the script has the option when they give the file name, they could just give a path. It doesn't just have to be a file name, it could be a whole path to that place. A relative path, an absolute path, those would be okay. But I want to write the output file relative to where the script is, right? So like maybe we're going to put the script in a subdirectory, and then maybe we're going to run this multiple times because maybe some parts will fail and we need to run parts over and over again. And so the first time I run it, I want to put the outputs in like the pass1 directory. And the second time I run it, I want to put the outputs in the pass2 directory and so on. So I want the output files to accumulate in a programmable directory. I don't want this directory to be hard-coded. I don't want it to necessarily be literally just the current working directory. I want it to be a configurable place. So oh, I got a little ahead of myself there. So I don't think we're doing subdirectories yet, but I want the output file to be in the current working directory. We'll then do the sophistication of letting the output subdirectory stuff happen. But okay, but here's the idea. The input can be in any place. The output is going to be in the current working directory. So if the path name for where the input file is has got directory stuff in it, like this, right? Like if it's somewhere else, or if it's an absolute path, right? Right. If we're going to produce the output file in the current directory, we just need to get rid of all that stuff that's at the front of the input file name. And base name is the tool that does that. We just give base name the file name we're told that the input file is, and base name will strip off all the directory stuff in front of it and just give us the bare file name part. And then we're going to capture the output of that with the process capture like we've done a couple times before. And so out base shell variable will be the input file name minus just the bare file name, none of the directory stuff leading up to it. Then we can trim off the FASTQGZ suffix on that and put on the thing we want there. And so our out base will be a relative path, just a current directory. The input file is pointing wherever it is. It could be anywhere. That will allow us to run this thing without necessarily having the input and output files have to live in the same place. Okay. The next thing you have to do is that anything that you did in your interactive session to set up your environment, you have to repeat, because when the job system kicks off the job script, that starts with like a fresh universe. Like if you were doing like a fresh QRSH into a new compute node. So if you're using module stuff, or you're using virtual environments, or for you guys, it's now this, right? Because you guys are using mine now. So this is your version of the environment, but we've decided now that you guys are using mine. So this needs to be changed to this, because you're getting the environment not from your own place, but from my place now. But you need to set up the environment as if you were doing it in a fresh session of your own. So for us, that means the load GCC, the load Python, and the activation in my copy of the virtual environment. You do need this one extra line here, which is kind of unfortunate. It's just sort of a magic line. When, for whatever reason, I never got a chance to talk to the administrators to find out why this is true, but for whatever reason, when job queue jobs start, they start in a really Spartan shell environment. They don't even include the module command in like the JavaScript environment, which makes it difficult to even like bootstrap up something bigger. So this source bash RC line just kicks things off and gets you into an environment that is very much like when you QRSH fresh into a node. In particular, it makes module work again. So you need this yellow line pretty much all the time. And it's just, without it, like the module loads wouldn't even work. That's just a piece of magic you need to have for Hoffman. Then we have the actual meat, right? All of this is just preparatory work at this point. This is the actual command that does anything, right? And so what we do is we call bisolve bolt align, give it the same command line parameters we did in our test run. So we give it the DB there. And notice that here, I'm actually specifying the database not as a relative path. When we ran it interactively, we had this. And that's because we were starting off the bisolve bolt align command in a working directory where the index directory was right there. But now, since we want to be able to decouple where the working directory is from where the script is and stuff like that, it makes most sense to actually just give the absolute path to the index, because then it doesn't matter what the directory is right now. This will always name the index no matter where it is. what the CWD is right now. So this makes the script and the database parameter not depend upon the script being run from the same directory as the database. This option is the same as before. This option is the same as before. We will do the little refinement that we talked about on day one, where we tag the files with like in progress, and only once the command that generates them succeeded do we rename them without in progress, because that will help us detect failed cases. And so we just tell bioself-bolt to name the output file whatever it was going to be, -- in prog. And remember, bioself-bolt is the one that puts the .bam on the end, so we don't need the .bam here. But that'll tag them kind of within progress. Bioself-bolt doesn't care what the output file name is, but this will create the output file name with sort of that tag on it. This number of cores is one of our command line arguments. That's okay. That's all good. That is the alignment command as we pretty much ran it on the interactively. But now we'll follow that day one pattern where we do the double ampersand, which says that only run the command that follows if the command on the left had an exit success that was successful. So now we rename the output file from the one that's got the tag in prog, and we remove the in prog tag and just rename it with the .bam there. And we don't have to do this, but often it's nice to capture the standard output and the standard error of your pipeline into separate log files. Now, the queue system is going to capture a standard output and standard error already. So like when we do these echoes, those are going to go into the queue system's standard output logs. Why separate out your main pipeline's standard output and standard into separate logs? It kind of helps you because there's sort of a difference qualitatively when you're figuring things out, what succeeded and what failed, between problems at the queue level and problems in the pipeline. And so it just sort of is an organizational help to us when we kind of look at things when this is done, that queue system level stuff, it will be in its own log files, and pipeline level stuff will be in its own log files. So there we go. That is the script. Now you guys are going to have to edit the script, like I say, because we changed the way the environment works, right? So go into, you're going to have to edit this any of the ways that you can edit a file. So for some of you, that will mean you download the file, edit it in local text, et cetera, and then push it back with your file transfer software. If you know VI, Emacs, Nano, you can edit the file directly on Hoffman. There's all kinds of ways you can edit files on Hoffman, but basically we need to make a little change to this file. I'll show you VI. So I'm going to VI that file, and it's going to bring me into an interactive editing of this file. And VI knows it's a shell script and has activated syntax coloring for shell scripts. And the line we need to change is this one, right? Actually, for me, it'll work because, I mean, the scratch is in the right place for me, but for you, it's not right. So we need to change the activation to be U scratch C cocus so that you guys are pulling it from my place. So I just did the edit using VI. I will tell VI to write the file, and I will tell VI to quit. And I now have a modified file. If I cat this out to see what it is now, you'll see that this has been changed. So I presume from workshop 1A, even you guys have some mechanism by which to edit files. So do whatever it is that you do to edit text files in Hoffman and make that change. And then we are ready to kick this off. And that's going to be where we end today, because we had such a battle getting bioself-bolt running. It's okay. We still have enough time, but we'll probably take all of day 3 now. So it'll be okay. So we are going to, it might not be a bad idea to test out this shell script before we actually kick off a Q sub job with it. So we can directly test it. We don't need to do the user bin time. We've already seen the statistics, so we can skip that if we want, but we are going to run this shell script. So also you presumably know from workshop 1B is probably where you first see shell scripts. So if you look at this shell script, you also know the one thing you need to do for shell scripts is to make sure they have the execute permissions bit set. So if I do an LSLA on the script, you'll see that it's got these X's. The R's are for read, the W's are for writes, the X's are for execute. Shell scripts need X's on them. And if you don't have it on there, you should have learned at some point the chmod command to add the X's. So like you can do chmod plus X, U plus X, A plus X. You may have seen like 0755 or something. There's different ways to do it, but you need to do something like this. If the X's are missing, then you need to do something like this. In this case, your X's should be there because the cp-p command you used to get this file, the -p, one of the things it does is preserve permissions. And so the X's in the source should have carried over to your copy. So you should have the X's already on there. But shell scripts need to be marked executable. That's why actually you see green. The default LS color scheme on Hoffman is to, like, gzip files somehow show up in red and directories show up in blue. Executable things show up in green and so on. That's the default color scheme they've got going on Hoffman. Okay, so we need to, and then there's the issue of the path, right? So you could give the absolute path to the script to run. So this is the directory we're in right now. So I could sort of give the absolute path to the script and then give the arguments and so on. That would work. I can't just give the name of the script and give the arguments and have it work because the directory I'm in now is not in my path. You should have learned in workshop 1B about the path. This is the directories that the shell looks for commands. This directory we're in right now will not be part of your path. And so the shell will not be looking in this place for commands to run. And so just giving naked the name of the command will not work. But you can, just as you can give an absolute path to the command, you can also give a relative path. So since actually these scripts are in the directory that I'm sitting in right now, I could say / this. Whoops, if I type it right, that will work. So we can name the script like this and the shell will find it. Probably in workshop 1A, you should have learned that dot is a name for the current working directory. So that / is a way to tell the shell, okay, it's in the current directory. That's where you're going to find it, even if it's not on the path. Okay, so that's the name of the script. Remember, the first argument is the number of cores that we want it to run at. This could be 2 or 3. The session's 3 right now. I don't know, for whatever reason I said 2 here. Maybe because the core usage was so low on our stats that we just did on the first test run. And then we have to give it the name of the input file, right? So like that's the second argument that we designed this shell script to take. So this second argument needs to be a file. Why don't we do part 2? Because we've already tested part 1. So why don't we give part 2 of the first sample? This first sample is the 1207. Second sample is the 1208. So why don't we do part 2 of the first sample is the input file. So that's the 2 command line arguments to the script. Here we're saving the standard output and standard error in 2 files. If we just wanted to see them go by on the screen, we don't have to do that. So really to test the script, this is all we really need. So there we go. So there's testing, ready to test the script. I'm going to hit return. And presumably this is running. Actually, you see the log message there out of our script. That's this line there. Okay, that's this line produced this output. And we're probably, at this point, we're probably in the bisulfite align. It's just that we haven't gotten any output yet. We know that it takes a few seconds for BWA to crank up and start giving some progress information or whatever. So we'll give this a minute or two. We're at 4:30, so we need to stop. But basically, we're just hoping that this is working. So then we'll open tomorrow with running it in QSub. But if you've got a few more minutes, you can just try the QSub right now. It should work. And once the QSub works, all we need to do, basically, the simplest thing to do is to wrap the QSub in a for loop, right? So if we got 42 parts to do, and we know how to do QSub once, we can just put a shell for loop around that and do it 42 times and do the QSub 42 times, and that will in-queue one job for each of the guys. And that will work just fine in this case. That'll work up to a couple hundred jobs. It doesn't work great once you get over like 400 jobs. It's too slow, and I think there's a 500 job limit for most of us. And so the last thing to do is to just show you a better way than just a for loop over the QSub. So we will do that tomorrow. That's the job array part. And as part of doing job arrays, we will actually have a very nice system for handling multiple variable arguments per command rather than right now we just have a single file name. It's pretty easy to handle. So the shell for loop can just do like over a shell pattern to get the list of file names. But in general, you have sort of multiple changing arguments in a pipeline, and our job array system will handle that quite nicely with a multi-column configuration file. Like you could make that in Excel or something. So we'll see that tomorrow. But I guess it takes 5 minutes or so. So anyway, so if you got to go, you got to go. But hopefully, if you if you try this, you should see that work and run now. Okay. So we'll see you tomorrow. And we'll try to make up for lost time since we had this battle today.
Thank you, Sean.
Thanks. Let me stop the recording.